Hello.
Malena, just speak up rather than writing in the chat.
Thank you, David. So, welcome to Friday. We just had 5 minutes of session that we didn't record. We're sorry. And
Show that it's recording. Oh, no, sorry, it is. Okay.
Magda.
And basically, we are again making the comparison between brushless DC, and steppers. Steppers, they have low efficiency, they are really heavy usually. And a funny fact about the steppers is actually they behave the opposite way as the brushed and brushless. A stepper, torque, speed. As long as you increase the speed of a stepper, you reduce the torque. So actually, it's the opposite. You start with a really high torque. As long as you increase the speed of a stepper, you reduce the torque. So actually, if you want to run a stepper at really high speed and still have enough torque to control a high mass, you need to overrate and actually take the design of the stepper to be thought in the minimum amount of torque that is going to be the highest speed. And that's quite important because, for example, you have seen some 3D printers, because usually it's a common 3D printing, common problem in 3D printing, that you are moving slow and the machine is working well. But suddenly you are moving fast and the machine starts making a back print and loses steps. That's why, because at the highest speed, it doesn't have enough torque to actually break down and accelerate the other direction. So actually it loses one step or a few steps. So the brushless, when you buy one brushless, usually they are defined by the diameter, the height, and the number of poles, the number of stators. And usually depends also the number of magnets, because the number of magnets usually relates to the stator, but not always. So when you buy a brushless motor on the side, for example, let's go to a classical brushless right now that I know I use them this size a lot. This is a really common size in drones. That's why I know. Yes. So you can see it says MT, that is the model number of the manufacturer. It says 2204 2300 kV. Actually, this is the 2204 is not the size of the outer size, it's the size of the stator. So it's telling you what is the size of the power drive train of your motor. So it's 22 millimeters in diameter, 0.4 in height, and it's stating also what? The revolutions per volt. That is what is the revolutions that this motor will deliver based on the voltage that you apply to it. So if you run this motor at 1 volt, we just multiply, sorry. Actually, we will rotate it at 2300. Actually, this motor, because of the coil design and the thickness of the wire, will not work at that voltage. And you only can know the working voltage of your motor based on the data sheet. So I know these motors are rated from 7 volts. So we multiply. So at minimum speed, this motor would rotate at 60,000 RPM to 16 volts. So this motor will rotate, sorry, 10 less. Yeah. So actually this motor will rotate between 15,000 RPM to 36,000 RPM. That is a huge difference.
Edu, yesterday you said that over this they get hot, and I was reading online that apparently you can feed them more volts just if you cool them down. Is that true?
Yes. Okay. So actually the motors the rating of voltage of motors depends on the wiring of the stator. So these wires, this is copper, and this copper line is covered with a resin. That's why you don't make a short automatically between all the wires. Let's say it's a copper that is isolated, but with a really thin transparent sheet. So this copper gets hot when you conduct electricity to them. And the rating of the motors is based on a lab condition. Let's say a motor without forced cooling. So let's say we are running this motor at 16 volts. This is the maximum rating of this motor. So this motor is, actually I have a few of them here that I have burned. I think I can show you. It's going to be difficult, but I don't know if you see well. Some of them are black, especially the one that is high on the top. So what happened is the copper has a heat dissipation power. So just because of the material properties, when you heat up the copper, it dissipates power, heat at a certain speed. And in this case, what limits the voltage, working voltage of the motor is the heat dissipation power of this motor. So if this motor is, let's say, 300 watts at the maximum, it says the body of the motor, the copper, and everything is working as a heat sink. So at 300 watts, this heat dissipation makes the motor reach, let's say, around 60 degrees. So above that temperature, the resin that covers the copper gets degraded. And by getting degraded, let's say we are running at 18 volts and we are running for like 3 minutes. So this is getting hotter. That means it's not anymore at 60 degrees. It's going to be at 80 degrees. At 80 degrees, the resin gets burned a little bit, and by getting burned, makes a short on the copper. And by making a short on the copper lines, what you do is you don't have any more 10 turns on one stator. What you have is 1 turn, because all the copper is short on itself. If all the copper is short on itself and you have only 1 turn, because the whole line is working just as one, not as 10 turns, you have less resistance. If you have less resistance, the copper will get even hotter, and actually that's a cascade of heating collapsing. So in the moment you start burning a little bit one of the coppers, the problem just gets worse and worse and worse. So what happened, for example, these motors, as they are protected, let's say by resin from short circuits, actually you can run brushless motor underwater without any issues. Not salt water, but...
Yeah, I was going to ask this, are they waterproof then? There's no other electric components in it?
They are not electronic components, and all the wires are electrically isolated. The only thing that is not waterproof are the bearings. So if you use pure water, let's say with any other component, they will not get rusty or they will last a lot. But let's say you can run these motors on a lake, and of course the life length is not going to be like 3 months, but it's going to be easily like 1 month. Actually, you have some projects that are called the open sub rubber. Arduino. I always look for Arduino and it always comes. Submarine. Marine rubber. That is a really nice project. This one uses brushless motor, just straightforward, touching the water. I don't know if you can see actually the motors, but you look for the project, they show the data plans and everything, and they use just a standard brushless motor with low kV, so they rotate slowly, and that's it. So how would you drive these motors? Well, first let's finish the datasheet of a brushless motor. Let's go to hobby key 2204, because I know this usually is quite a standard. You have all the sizes of this. You have motors this size, and you have motors that are actually 3 grams, really, really small. So this is a standard motor. This says, okay, the RPM the voltage, the working voltage, the thrust. This is because they calculated the thrust with a propeller, but actually you can equivalent this to torque. Poles, 14 poles. It means we have 14 poles on the stator. Usually more poles means less torque, but higher kV and more control over the rotation. You have the different dimensions and the weight. Something that is quite important that, for example, they don't state here, that is really bad. Let's say to specifications. Actually, this is the worst data sheet ever. It's really important that they state the, okay, 22.004, 2300 data sheet. Images, please. Yeah, this. They state what? The pool is not important, it's for a propeller, but they state the amperes of consumption on a voltage. And let's say at 11 volts, this motor has a consumption of 13 amps. Actually, brushless are really ampere demanding. They means they are really hungry for amperes. They have a really amperes consumption, really high. And in watts, this motor has 145 watts. And they give you something that is really important, that is the efficiency. So that means that this motor pulls 2.96 grams per watt. That means where the motor is more efficient. This motor is more efficient when you're working at low speed. Actually, when you're running it at more or less 2.5 amps, that will be like more or less 7 volts, the lower range of the motor. And actually, this one provides 4.72 grams per each watt of consumption. So that means if you want to run this motor at the highest efficiency, you don't need to run it at the highest speed. You need to run it slightly slow, just a little bit before it starts moving. Actually, that's the perfect condition, but that doesn't mean that this motor cannot provide more torque. It's a little bit confusing, but something that you always need to worry when you design your motor is actually the maximum power consumption. Why? Because the brushless needs to be driven with an ESC, that is an electronic speed controller. Nowadays, there are a lot of types, and there are even open source alternatives and designs for speed controllers. A speed controllers basically is a double transistor. It looks like this. It's a triple H bridge that controls the 3 power cables of the motor. And the control of this needs to be done at really high frequency. I think it's usually 100 megahertz of control if you want to run it at the highest speed control. So that means if you have connected, for example, 3 brushless motor to an Arduino, you will need to run not only 3 triple H bridges for it in total. That means a lot of wire. So right now, like as Neil stated, China has developed since long time ago. Right now, there is more than 10 years of DIY market evolution and like consumer markets, these speed controllers. So basically they are integrated. What? Actually, it's an 80 mega 85, 80 mega 8A. Actually, this is the same chip or really similar to the chip that is in Arduino. So inside each microcontroller, each speed controller, you have your own Arduino that is programmed with his own firmware to just control the H bridge, the triple H bridge of the speed controller. And how you control these guys? You obviously you don't want to implement a really complicated networking because maybe you have like 200 speed controllers and 200 motors. So they simplify them enough that the input signal that this speed controller takes is what? PWM, the standard PWM digital signal. So actually you control the speed of the motors, the speed of the ESC with a normal PWM signal. Inside these guys, right now, they used to be 8-bit speed controllers. Right now, you can also find them in 32-bit and 16 bits, but that is just depends on what you want to do. These are the typical firmware that you can load into these little guys, depends on the microcontroller that you use. So actually, you can pre-program just the speed controller to behave as you want. And actually, that is something that is quite common. For example, BLE is called BL yeah, configurator. So actually, you connect just with an FTDI, and you solder the pads to the speed controller, and they have some interfaces that you can actually adjust what? For example, temperature protection, Benji. So you can actually discharge the motor, not if the motor is getting hot. In this case, is the triple H bridge is getting hot of the speed controller. So you can actually cut it by temperature. You can accelerate at the highest rate, but if it's very too high, you might burn your motor. Or there are a lot of different types of, actually, for example, the frequency, I was wrong, it's not 100 megahertz, it's 24,000 kilohertz. That's actually really, really fast in the timing control of the motor. And something interesting is when you rotate a motor, a DC motor, when you turn it down, the motor keeps rotating, no? If you reverse the polarity, the motor will break. Actually, that's what Óscar was saying. If you don't break the motor and you just take energy, you can actually take it as a motor, as a generator. But also, you can take it as a brake. And actually, Xiaomi scooters, for example, that is something that you have seen every day. One of the wheels has no brake. Why? Because it uses what is active braking. That is actually counteracting the pulse and the pulsations to actually use the motor as a brake. So basically, if you are running in front, if you want to brake, what you need to do is run the motor backwards. So actually, as the motor has inertia and is pushing you, usually a person of 70 kilos, it cannot hold that amount of torque at once. So it does is slowly start sending impulses for the opposite direction to have what is called active braking. Okay.
Edu question. Does the shape or length of the shaft have anything to do with like the torque or the strength? Or...
Yes, exactly. I have on my page here. What is the motor? So usually, this is batteries is the next thing. Yes. So actually, motors with taller motors, let's say the two numbers higher, they are meant to have more speed. Sorry, the first two numbers are the diameter. Bigger in diameter usually gives more torque. Higher means more revolutions. So usually brushless motors are defined by tall, short, and big, pancake, what we call pancake brushless, that they have really a lot of torque, or thin and tall, like a person. Actually, that one is designed for speed. If you have more or less a proportion of same, that is a motor that is called same multipurpose. Yes? So when you design, when you look for ESC rating, these speed controllers are rated on different values. This is the most standard. For example, what you want to look for is a speed controller rated more or less 20% more than the maximum amperes of your motor. Why? Because let's say I have a motor that consumes 50 amperes, I might have some peaks of 70 at some point. And that will not burn the motor because it's called peak loads. These motors can absorb higher amperes at some, like for 5-10 seconds without getting burned, because the heat dissipation doesn't increase constantly. It just does for a spike, for a moment. So we happen the same with the speed controllers. We want to have always a 20% higher rating of the amperes. Also, the speed controllers are rated for certain voltage. So if your motor runs at 12 volts, you need a speed controller that also works at 12 volts. That's something kind of logic. And you have another option that is actually if the speed controller has BEC. What is a BEC? A BEC is actually this speed controller also regulates power and provides power out. That means, for example, this is the, okay, I hate these things. This one doesn't, and this one, BEC. What is the BEC? Yeah, here. So actually, this is the speed controller. You have the motor here, and you control with a data signal of PWM. With BEC, that means the red wire, the positive, also provides electricity. And that is the BEC rating. So actually, you can use the speed controller to power all your circuit because they have an integrated, let's say, power supply or power regulator. And actually, the BEC electricity at this circuit has to be really low noise. This BEC is already Arman filter, has already an LC filter inside all the speed controllers. So actually use them as a BEC, they are quite nice. And as these speed controllers have really high rating, the regulator is really quite powerful. So usually the BEC in most of the desk is around 1 and 2 amperes. That's a quite good electricity. You have another type that are the optocouplets. Yesterday we talked about the relays and the opto and the SSR. Those ones are opto-isolated. So ESC, opto, couplet. So basically those speed controllers, they don't have power, they don't provide power, because if you provide power, you cannot optocouple, but inside the data is not connected physically to the speed controller. Has also a small LED and a light sensor to actually have the data connection unwired. And that is important when you run big brushless, because big brushless have something that is called, and actually it's all the motors, something that is called back EMF. That is electromagnetic noise. So when you store a motor rotation, you are producing, and you don't actually push it, it produces spikes on the voltage because actually the motor is still rotating. And that produces a lot of noise. And actually, bigger the motor, more EMF you will have. And that, if you are running a really sensible circuit, if your power drive frame is really powerful, you have a lot of problems. It will actually make your microcontroller reset. So actually, for high power drive trains, you want to have everything optocoupled. But this is only when you design big systems. Let's say a electric go-kart, probably, I don't know Xiaomi scooters, but they probably will optocouple all of these kind of things. I will say that this EMF problem is meant for systems that they are more than 200 watts. This is just an estimation that I think about, like my logical estimation, but I'm not sure of this. But most of the big power drivetrain systems I have seen are opto-isolated. So this we have done, this we have done, this we have done. And we can go to actually how to drive these little guys, or any guy, like a DC motor, a brushless inverter, and your own circuit. But before driving, let's finish with another type of DC motor that is actually DC motors with encoders. There are different types of motors. We have DC, we have brushless, and we have steppers. All those motors are what we call open loop. Any clue what is open loop?
Open loop is when they don't know exactly where they are, and closed loop is when they know where they are, like when we look in the machines that they didn't know and they need the pieces.
Exactly. Very well, David. So basically, for example, we are sending voltage to a motor. Just simple example, a DC motor. We can estimate the revolutions that the motor is rotating because of the datasheet of the manufacturer, but we don't know exactly because for some applications we want to have really exact RPM control. For example, a DVD writer, or as Roger said, a floppy disk. We need to rotate at the perfect speed. So for that, we need to use what is called closed loop motor control. That is enabled in some way, usually it's by hardware, control over the speed or positions of the motor. It's really common to find them in DCs. So how to encode things? Usually what you have is on the back of the motor, on the shaft, you have coupled a rotating disc that could be magnetic, sometimes it's optic, and you have literally this physics shape. And what you have is a light, and it's bouncing or going through the holes. And by doing that, actually you can count steps. It's the same as if you cover half of your bicycle wheel, you can only see in some zones, no? But it's the same in a really small scale, and usually it's done with a lot of timing. So with this, we can actually control the speed because we can see, we see, we don't see, we see, we don't see, we don't see, we don't see. So actually, this is just a encoder. It's actually a endless potentiometer. If it's a light and magnetic potentiometer. So with this, we control the speed. If you want to control the position, you need double of this. One, because the one needs to be a little bit disaligned among the other one. Why? Because you want to know if you are rotating. If you have one, you don't know if you are rotating in this or this direction. You can only see or not see. If you have two, you can only see or not see. But what you can do is look at my face. I'm the light. I can know if this one has hide my face faster than this one. In which order? So like this, I can know which one has reached the sensor, and by so I can interpolate and know if I'm rotating clockwise or counterclockwise. So if you have double encoder, you can not only specify and control and read the data of what speed we are rotating, but also we can know the direction. Usually the encoders are most of the times doubles by defect. And they look like this. For example, this is a magnetic encoder. You have optical encoders and different types. The optical encoders are more obvious on the way that they are built because we can easily understand them. Optical encoder, optical encoder, optical encoder. Thank you. Oh, it's a like old vinyl disc, let's say, like the ones that they use for the first computers. That is a two-hole plate that we see will push light through the light sensors. So the wiring of a DCF encoder, where is the DCF encoder? It's actually you have the power and negative of the motor, and you have what? The wires of the encoder. And this is just a standard encoder that you can easily really see DC encoder, encoder, Arduino wiring. You can easily wire them and control the speed. Okay. I don't know why, but usually it's not stated like that in Arduino. I have a video here ready. So you wire the analog sensors because you have two analog sensors, one encoder and the other one that is slightly shifted, so you can know the speed, and you have the power one. And by so, you are able to estimate, yeah, like this here. You have the motor negative, the Hall sensor, the power for the Hall sensors, and the sensor 1 and sensor 2. So you wire them, and you can estimate in a really accurate way exactly the revolutions. And you have analog signal you can control in a closed loop. Actually, closed loop control is not automatically. We have to do what is done error prediction. That is PID control. Because Oscar will go deeper into this part, but we always need to do PID algorithms to control this in an accurate way. The last type of motors that actually I don't think you will work now with these ones are what we call servo motors, industrial servo motors. And I state industrial because it's not the same as an Arduino servo. Actually, servo usually comes from servo motor Arduino. They are these kind of things, no? But if you look for servo motor industrial, is completely another league. Actually, it looks really similar to a stepper, but it's not a stepper. These motors is a mix of a brushed, a DC with encoder, a brushless, and a stepper. So, and it has the best parts of both three worlds, and the worst parts. Irene.
Is this the one that they're using it in the robotic arm?
Yes. 1 second, guys. I have to close the window. It's really noisy. So these motors, they have the best position control, the best torque, the best speed, but they are heavy and really expensive, really expensive, and they have the most difficult control system of all of them, because you run them as a stepper, you control them with encoders of a DC, and they have their own firmware like the brushless. So that means inside these little guys, they have the coil wiring of a brushless. So they can provide really accurate control without but by using all the wires at the same time, because steppers, we only use half. Actually, servo motors uses all of them all the time. So they got the maximum power by weight ratio torque. They have the aesthetic lookings and the physical build as a stepper, because you want to run them inside and the magnets outside. So they have really high magnetance and they can hold the positions really well. They have encoders on the back, like DC motors. And they have their own control boards embedded, because these guys, they run their own software inside. And usually the software control of a servo motor is one of the most difficult things to get, firmware. And just an state of, you will not find, because it's not something that you usually find. It's really industrial device. Actually, for example, you see just by the prices of servo motors, this is the smaller servo motors that you can buy, usually. They equivalent to an EMA 34 and 23 in size, and the cost of these ones, they are now getting lower, but it really starts from 200 euros and up. In the lab, we have one servo motor. If someday we open again, you can try of it. And actually, the servo motor we have is the called servo.
What is it used for?
Actually, last year we used as a stepper, but with really high torque. And actually, the first time we tried and we switched it on, what happened is we control it and just switch it on without acceleration. And what we did is actually the motor is more or less this size, slightly bigger in a square. So actually it's quite heavy. It weighs more or less half kilo. The motor jumped like 30 centimeters in the air. just by the own revolutionary torque. Actually, almost breaks the computer one of the screens. So actually, those motors are fast. They accelerate really fast. They have a lot of torque, but they are more difficult in the control. And actually, we bought it, but we are still, as this is a Chinese servo stepper, and that's why we could afford it, because it was cheap. The information actually how to control it is not really clear. So we are trying to guess. We know how to use it as a stepper, but not exactly as a servo motor. So inside they look like this, and actually there's the best motors to get, and the robotic arms and really industrial devices uses this kind of motors. Also because they are almost maintenance free. And in theory, theoretically, they are equally as a servo motor. In the logic, you have a control system, control PCB, and you have potentiometer. In this case, it's not a potentiometer, it's encoder. But in the behavior and in the logic and how they behave, they are the same. But these ones are endless. But in the mechanical realization of them, they are different leaks, completely different leaks. And the cultron of them is also completely different. And these servo motors, they integrate already the control algorithm, the PID control. You don't need to do it externally. They do it on their own. I have a video of PID control somewhere. Let me see. Boop, boop, boop. What is the motor? Yeah. So what is no, Oscar, you're gonna do this part. Let me finish on how to drive these things, because we have seen we can have a lot of motors. We have sometimes a lot of amperes. We have a lot of voltage, sometimes really high voltage. Actually, normal DC motors, Cuco, sorry.
It's the longest one of the day as well.
Yes. So usually the working voltage of motors is in DC is up to 42 volts. It's not that common to see higher than 42 volts. But in the standard, in electronics, in consumer and DIY electronics, we always use 12 volts. And if you are looking for higher and more performant applications, you use 24 volts. Sometimes you can find 36 volts, but it's not that common. So how we control this? With batteries. You know what is a battery, no? Actually, you have batteries everywhere. Batteries, really? Sorry. There are a lot of types of batteries, and each one has its own purpose and different applications. We are really common to see this type of batteries. These batteries are usually NiM. What is the photo? NiCd, NiEm, and NiHm. The batteries are determined by the chemical composition, because batteries have basically a chemical reaction inside. And by the chemical reaction, you can estimate if you can reload it. It means you can reuse the battery because you can charge it and discharge it, or they are just one-time disposable. I will not talk about disposable batteries because I'm really against them, and I think these are waste of resources of the world. So let's go just with rechargeable batteries.
Which ones do you don't like?
Disposable ones. They don't make any sense nowadays.
Yeah.
At any point, not even before, like they didn't make any sense just because of the industry and the world is fucked. But so actually we can recharge almost all the type of battery, but the ones that are disposable, they just fabricate in a way that they are bad and they cannot be recharged properly. If you try to recharge a battery that is not rechargeable, it might explode. So quite be careful when you work with batteries. The batteries are determined by the volumetric energy density. That is the total weight of the battery and the amount of electricity and the energy they can store. So that means, for example, we have the lead acid batteries, that is commonly known as the car battery, the big packs, or the black square boxes, they have a low capacity of storing electricity by their own weight. That's why the car batteries, I don't know if you have ever changed your car battery, is really heavy and actually doesn't have that much power. We have the NICD and the NIHM that before were used to be like the standard, like super high-end batteries. That is a typical battery, NIHM battery RC car that you have probably charged when you were kids. It looks something like this. No? You have probably charged this when you were kids. Actually, this is NIHM batteries. These batteries have a good power electricity storing by weight ratio, much better than the lead acid, but they have a problem. They have memory. And we will talk what is memory later. And we have the batteries that are common in every electronic device that we use right now, that are the Li-on, Li-po, and Li-ion. That is the lithium battery in general. You have lithium polymer, lithium ionized something. I don't know exactly the terminology, I'm sorry. But these batteries, they can store a lot of electricity in a really small and light package. And actually, that's why our phones last a lot nowadays, because the technology in these batteries is good. But as you have seen, you know about the Samsung that exploded. No? There was every day.
The Note.
Exactly. Those batteries are really sensible to misuse. And actually, I don't know if you know, but the battery of the Samsung, the problem, Samsung explode battery defect fabrication. I don't know if I found out the picture. Yes, no. iPhone electronics. Okay, a normal phone looks like this. This black cells is the battery. Actually, this battery takes most of the part of the cell phones right nowadays. So the problem with that phone, for example, was that the design of the place for the battery was slightly smaller, 1 millimeter smaller than it should be. That means it was pressing a little bit the battery on the side. And when we are charging the battery, the LiPo batteries augment a little bit in space. And they were constrained in space, and by constraining them, they were heating up and exploding. Just because there was a 1 millimeter defect on one of the corners of the battery holder. So actually, LiPo batteries are the best, but also the more sensible and prone to fail.
And what about sodium batteries? Are they any good?
Sorry?
Sodium batteries?
Sodium batteries. I don't know too much about them. Sorry.
Okay.
So nowadays, LiPo and Li-ion batteries that are usually in Xiaomi Power One electronics are the best, and they can deliver a lot of power. More or less, a battery, the difference between both is that the lithium polymer has a soft package. It means it's like a metallic bag. And the Li-ion is enclosed on a metallic cover that looks more or less like an AA battery, but has a different shape, different size. So the Li-ion, see?
I just want to ask, like, I was looking for this lithium polymer, exactly 5 volts, but I cannot find it.
Because they don't exist.
Yeah, I think so. So in case I have to look for something like 6 or 7.4, I have to do the voltage regulator, right?
Yes.
If I want to use it.
Exactly.
Okay. Yeah.
So these batteries, the Li-ion, are determined by cells. But let's go to the simple one, just the battery itself. Li-ion has higher energy density. That means this one is the one that can store the maximum amount of electricity by the weight. But these batteries, they are encapsulated in a metal cover. So that means they are heavier compared to lithium polymer. But they can discharge more battery in a longer term. That's why, for example, power banks use Li-ion, because they can store more amount of energy. They are cheaper and they last longer in general. Lithium polymer is, let's say, the light version of the Li-on. So that means it's really light, but it's not protected at all. If you literally punch this battery, it will explode. In a chemical explosion, in case that happened ever to you, don't ever put water, because water reacts with lithium and makes the problem much bigger. Really much, much bigger. So don't ever throw water to these batteries. They have another problem.
What should you do?
Use sand, or you cover it with and put in a metal box and let it burn. Or use a chemical extinguisher. One mean for chemicals, that is a C-type. The working voltage of the batteries is weird, and how they are rated, because you know AA batteries are 1.5 volts. The small package of disposable 9, the square ones, are 9 volts. LiPos are determined by cells, and by cells is how many bags of battery they have. So a battery is determined by the bag size. That will be the amount of capacity they can store. So for example, this battery is 5,000 milliamps. That means 5 amps. One cell, the bag size is 5 amps, but one bag is always 3.7 volts. So the unit in voltage of a LiPo battery and Li-on battery is 3.7 volts. If you want to have more voltage, actually you run 2 cells in parallel. So that means you have one cell of 5 amps, one cell of 5 amps, and sorry, you run them in series, not in parallel. You run them in series, and by so you augment the voltage. But that doesn't mean that you augment the capacity. You still have the same 5 amps capacity, but at double voltage. You have 7 so. And basically what you do is multiply the number of cells by the volts, and by so you have the voltage of your battery. So if you want to have a 12-volt system, you use 3 volts. Why? And this is funny, but I will just make in a paint. I think it's easier. Batteries, they have different load when they are charged and when they are not. So they say the battery is empty, the battery is full. Empty, full. A LiPo battery, they always give you the middle rating, 3.7 volts. But a LiPo battery, when it's fully charged, is 4.2. And a battery cell, when it's fully discharged, is 3.3. If you run the battery lower than this value, let's say you leave a LED always connected and you never worry about the battery, if you go through this threshold, the battery will be damaged forever. If you charge the battery higher than 4.2, the battery will explode. So actually, LiPos are really sensible, and we never connect straightforward any device to them. We always use LiPo managing boards that are boards that actually control this to always keep the battery in a protected state. And actually, the LiPo managers always cut the battery at this, but the point where the battery gets completely damaged is at 3.0 volts. So why I say that a 12-volt system works with a 3-cell battery? Because actually we don't multiply 3.7. We multiply the maximum, that is 4.2 per 3. And that gives us what? 4.2 per 3. We have exactly 12.6 volts at fully charged. That is the circuit that you will have when it's completely charged. Usually, you don't need to worry about too much about this, but you have something that is the LiPo manager boards, and you have to use them for charging and discharging, and also meanwhile you use them. They are boards that you basically connect the battery, and you have the output pins, and they will manage everything, the charging, discharging, etc. Okay? So usually your electronic looks like this. You have another thing, how much power can you take out of the batteries?
Edu, quick question. Commercial batteries, I assume they have this board embedded in them, right?
Which batteries? What do you call commercial batteries?
Like this one.
This one, yes, they have one inside. Xiaomi power bank tear down. Yes, they have usually it's a circuit that looks like this, yes. And actually, let's say why some power banks explode and why other ones not is just because of this. Because on how good this board is designed. And how like they use cheap components and that by so they overheat in long term and they fail, and by failing they make the batteries destroyed, basically. It's quite important, like this part, especially with Leon and LiPo batteries. For example, you see this one. One of the things Xiaomi power banks in general are good is this. They have a temperature sensor to control the overheating of the batteries. So if they overheat, they cut down the electricity and they disconnect everything. That is quite important because LiPo batteries and Leon batteries, well, any battery when you use it produces heat because you are making a chemical reaction that is exothermic. If you run onto the threshold of the power dissipation, they can also overheat and explode. So more things on batteries.
Sorry, also a quick question. You are saying that when it's fully charged, it's 4.3 or 4.2.
Yes.
But if it's almost empty, then the voltage would be lower than what you intend to. So you will be undervolting your board, no?
Yes, exactly. That's why most of the devices, when they are running out of battery, like most of the electronics, they don't have a steady working voltage, let's say a fixed. They can work in a range. And usually the LiPo cells goes in the same range. That is for motors. If you want to have the same power continuously until the end of the battery, you need to embed a power step up and power step down circuit that keeps the voltage in exactly the same range. But you have a problem with that, Daniel, that is if the motor and for example, the circuit is consuming 30 amps, having a step down and a step down converter to have a steady 12 volts at 30 amps, that component is huge in size and in price. Those components are difficult and expensive to manufacture. So actually you don't run them, you never run them. That's why, for example, electric bicycles, when they are getting out of battery, they don't go fully at the highest speed. They cannot because they're running out of battery. So it's something that in driving trains, you assume is going to be like that. Because converting the power down at that amount of amperes is complex. Daniel?
I see. Thanks.
So we have a problem. How we determine the size of the battery? Usually it's more or less easy. If we have a battery that is how much? 5,000 milliamps, that is basically 5 amps, and your motor has a consumption of 20, you divide them. Your battery will last at the maximum, at the highest power consumption of the motor, 0.25 hours. That means 15 minutes. That is it. You divide the milliamps, the total milliamps of the battery by the consumption, and you have the time. Because the amps is amps per hour, always. It's the capacity of discharge. And actually that is the total capacity of discharge. But we have something that is called a speed of discharge. That is quite important, not when you run electronics, but when you run motors. A motor that consumes 10 amperes, that means you need to have continuous 10 amperes to the motor. And all the batteries are rated to have a maximum speed of discharge. And that speed of discharge is 1. So if you have a battery that is 5 amps, also this number is called C, 1C discharge. If you have a battery that is 5 amps, it can only provide 5 amps. If you push 10 amps, your battery will be damaged. You will damage the battery and probably will overheat because you are accelerating too much the chemical reaction, and by overheating, it will get to explosion. It's automatic. Luckily, some batteries, not the NiHM, have higher rating. Only the NiHM have a possible discharge rate of 2C, but depends on the manufacturer of your battery. They need to clearly state your battery is 2C. That means if the battery is 2C and I have a battery of 5 amps, I can multiply, and actually my battery is, even if it's 5 amps in total battery storage, it can provide 10 amps continuously. Because the rating, the IC rating, the C rating is double. That means the chemical reaction of my battery could be done at double the speed.
Is this how this fast charging?
Is not exactly, but yes. That's because lithium and LiPo batteries, they have wider range in the C. For example, you can find batteries like this. You see the number 25C. So what happens if we multiply 25 per 5,000 per 5? Sorry, what? No. 25 per 5. Actually, this battery is able to provide 125 amperes continuously, even if the battery is small. So actually, this battery can provide constant energy of 125 amperes.
For 2 minutes.
Exactly. For 2 minutes, but it's able to. So what happened? Why do you think electric cars nowadays, you have electric bicycles and you have like electric mobility in general? Because of the rise of LiPo and Li-ion batteries. Before, to run a scooter, Xiaomi scooter motor, you will need a whole truck of batteries just to drive it, just because of discharge rate of the batteries. Nowadays, you can pack much less energy, much more energy in a smaller package, because the Li-ion and LiPo batteries have higher discharge rate. And actually, one thing that is developing this field of high-end discharge rate batteries is the drone market, because you have seen the racing drone videos, and racing drone usually has a power consumption of more or less 160 amps per second at full blast. So that means the batteries, they need to be as light as possible so the drone goes faster, and they have the higher density. So actually you can easily find, for example, this is really common, 1.3 LiPo. Sorry, not 12, it's 120C LiPo. These batteries, nowadays, they weigh more or less 100 grams. They have a capacity storage of 1,300 milliamps. That means we have 1.3 in capacity, really small. But I have seen batteries that until a maximum discharge of 160. So that means a battery of 100 grams, that is half your phone weight, half the size, can provide 200 amperes. So always that you want to look for a battery, you need to look for the discharge rate of the battery. This is for LiPo. Li-ion, okay, sorry. I never think on these kind of things. Li-ion batteries, unluckily, they have better capacity storage, but they don't exist with high discharge rate because they are meant to have big capacity but slow discharge. So these ones, the common type is to have them in 1 and 2C, no more than that. You can only find high C application in LiPo batteries. And for example, you see the traditional, your old phones used to have these batteries. Actually, the state, the voltage, for example, this battery is a 3.7 volts, it means one cell, has a capacity of 700 milliamps, it means 0.7 amps. And this is the watts per hour. It means the capacity of discharge. Sometimes it's in watt per hour, sometimes it's in C. Depends on the battery manufacturer. But when you design a circuit, what you need to do is always think of, for example, let's say I have a wheel. I need to move 200 kilos. So I have a motor. Okay, what is the size of my motor? Let's say my motor has a power consumption of 12 amperes. I want to have a really smooth control. It's for speed because it's for a small DIY car. So if I don't have money, I will choose a DC. If I have money, I will choose a brushless because yes, it's better in general. So I have 3 cables. I have my ESC control. How am I gonna rate it? Okay, I know the power consumption of this motor, but this motor is 20 volts. So my ISC needs to be in a working range higher than 20 volts and with 20% more than 12 amps. So that means my ESC needs to be rated between 15 and 20. Basically, I will go out on the market to find out which kind of ESC I can find. Could be this ISO couplet. I don't know. If I can afford it, in general, it's better because you avoid noise. Okay, I have my Arduino because I love open source. I will make my own Arduino with Atetinis to control everything. How I power this? Okay, I know that I have 12 amps at maximum consumption. I don't think I will blast my car at the maximum speed all the time. I don't think I will go at the maximum speed like drifting over the streets. So I will estimate that I'll use usually half of the battery, half of the consumption, because I know is the maximum performance of my motor is the most efficiency grams per watts of consumption. So usually it's around 6 amps of consumption. I want to run my car for 4 hours. So that means I need 24 amperes of capacity of storage. Let's say I want to have a little bit of extra. I add 20% more or less. So I go to 30 amps of battery. Okay, now is the time that I know my capacity of the battery. I need to know my discharge rate. Okay, the maximum amount of amperes that I can have is 12. And I have a battery that is actually 30. I have no problem with discharge rates. So I can choose a battery that discharges at 1C. Why I will choose the slowest and the discharge rate? Because actually, when you increase the discharge rate, the battery increases a lot in price. I will say that doesn't double, but right now, LiPos, usually they are always 25 Cs. But for example, from a 25C to a 90C, usually duplicates the price of the battery at the same capacity. And also augmented the C, the LiPos get slightly more heavier. So I will choose 1C. Okay, I want my battery to last a lot of time. What I will choose? Neon or NCD, Leon, or lithium polymer. Actually, I can choose all the types because I have lower than 1C of discharge rate. If I want that the battery lasts years, but I don't care about the weight of my car, I will lose lead acid. I plan my car to I don't plan to run my car every day, maybe once a month. I will never choose these ones because these batteries have what is called memory effect. You can store these batteries, discharge or charge, because they will remember the last state of the battery and they always will tend to be in that state. It's something quite complicated, but it's called the memory effect. And actually these batteries, type of batteries, have that problem. So not as one nowadays, we try not to use them a lot. So I want my car to be light, so it has good control. So I will try to choose lithium polymer and Li-ion. Which one I will choose? Actually, I can choose any of them because I have 1C discharge rate. What happened? I don't care if it's slightly heavier. Actually, the weight per ratio of both is really good. What happened is these ones, they have longer lifespan. As they have casing and they are protected, the life cycle is much longer than the lithium polymers. Basically, they last more years, charging and discharging, because they are less stressed in the mechanical composition and how they are built. So I will choose lithium batteries just because I can make my battery pack last at least a couple of years without any damage, and while keeping my low weight per ratio of my car. Last part, yes? Sorry?
I was going to ask you something about, I saw that Tesla cars have these 18650 batteries things. And
Sorry?
I was wondering, because when you were talking about the what's it called? Capacitance? Or...
You mean this one?
Yeah, I saw Tesla have all these ones, but if they're 1C, is it just, if they use, for example, 100 amp, you just need to put like 100 of these in parallel for it to work? So you can either put loads of batteries in parallel or have a high capacitance.
Exactly.
Okay.
So actually, this is the common size. This number means states the capacity, and usually not the capacity, but the shape of the battery. This is the quite standard lithium batteries right now in the market, the most standard one. There are different types, but this is the most standard one. And actually, this is what Tesla and most of the car manufacturers uses for the battery packs. And actually, the battery floor is just these ones stacked, millions of them on the floor of the car. Why they use this one and not the LiPo? First, because this one are hard cased, that means they are protected against impacts. In a car is quite important because of higher order. Second, the life cycle is longer. So that means they will last more years. You don't want that you have to replace the car battery of your like $50,000 car every 2 years. That's the same that happened with a phone. So actually the LiP phones, as they have, they have the predicted that you have to change the phone because they want the industry every year, or they try to, they put LiPos. So the battery gets lighter in theory, also it's more performance, but basically they last less time, last less time. So in cars, we don't want to have that problem, so we use this kind of lithium batteries.
But Edu, you're driving on top of a huge bomb then, right? Because if they can explode, it's like plenty of them there.
Actually, now that we are getting electric cars, all the firefighters are getting manuals on actually how to extinguish these kind of cars and how to proceed when they open these cars, because they cannot just go in with the clamps and just cut the frame to take it out, because if they clamp in the wrong part, the battery will explode. But these car manufacturers are getting really, really worried about this. And actually, they have a few cases that one Tesla burned because it hit one rock on the highway at high speed and it broke out one of the batteries. But that is really uncommon case. But think about cars. You are running on a tank of 70 liters of gasoline. So that actually, I will say that a battery that is protected with like 3 plates of titanium casing is much safer than a plastic tank of gasoline. Just my personal thoughts, but and actually one of the things of batteries of electric cars is the floor is completely metal and it's really dense. Actually, the crash test of electric cars in general has much safer protection than normal cars because they have a really reinforced floor that increases the stability and the rigidity of the whole frame on the occupancy of the car, inside the occupancy. So
I
actually,
think the 3 Teslas are the 3 most secure rated cars.
exactly. And also this reduces the center of gravity of the car. So actually it's really difficult to roll over an electric car because the center of gravity is really, really low, and they make them really stable, and actually they make it nice to drive and to drive them because the mechanical, like the dynamic behavior of electric cars is usually the best one. It's the idea. It's the lower center of gravity. It's not that heavy. It's really high power, really fast, and actually all the electric cars can deliver are the highest acceleration that you can find. For example, the cheapest electric car that you have right now, the one of the Renaults, the Zoe, has acceleration more or less of, I think, takes 6-7 seconds to reach 100 kilometers per hour. In a normal car, that's the cost of a VW M3. Like the acceleration of those cars is really, really, really good compared to engine cars, like because they are meant to actually speed up a lot.
And are they still like limited by software? Because you said earlier that usually they do this speed while still being limited.
They are limited, really limited. And actually by limiting is how also they manage to make the battery last longer, have more range. And that's why the Tesla has a mode that is the sport mode and the ultra sport mode. So the limitation is lower, and that's when you go fun on the highway. So
do you think we can find another way to store energy in a more efficient way? Because now we take a lot of spaces to...
I heard about nanotechnology ages ago about batteries.
Now they are getting kind of lithography batteries that they increase a little bit the power by ratio, but the storing energy is actually one of the biggest problems that we have as humanity right now. We do it in a really nasty chemical way that we cannot recycle, neither reuse. We are not efficient at it. Actually, it's one of the biggest problems.
Biology, guys. That's the example.
I was talking about sodium battery earlier because it's made out of like salt or some, so apparently it's super cheap and quite ecological, but I don't know how good they are or how efficient.
And what do you mean by biology, Roger? What do you have in mind?
Well, like see how calories in the body is super, super efficient, right?
Yeah. Right.
Nice. I saw, Óscar, that you put how to build your own 16 packs. That's pretty nice. Last thing is connectors. It's something that nobody thinks about, but it's important because basically you are driving a lot of electricity through wires. And so you need to connect things. The thickness of the wires also need to be calculated. And this is something that you say, okay, this is if I want an electric car, etc. Just driving a normal stepper that you find in the lab or a DC motor, I have seen like this every year, a lot of students burning out the circuits, the wires, making smoke just by driving small DC motors. Like everything you drive something that drives more than 100 milliamps, that is basically any output, mechanical output, you need to design the wires accordingly to them. I don't know, are you there? Because I see you frozen. I don't know if you're steady or the camera is frozen. Hello?
Yeah, we can hear you.
Oh, okay. I don't know. You were all really like in the same position.
You put us to sleep.
Yes. So where gauge calculator is something that is not that difficult to do. Just look for DC. AC works different way. Wire size calculator, and basically you output your amperage, your voltage, let's say 20 amps, and the length of the wire, because the length of the wire augments by resistance, by the length. The resistance augments by the distance of the wire. Longer the distance, higher resistance. So you need to augment the diameter, the section of your cable to reduce the resistance. So if I want to run for 1 meter, 1 feet, let's say, that's 3 feet. I want to have a drop of 2%, that is quite common, until 5% is more or less common, not a big deal. You need to have, for example, a 22 gauge. I will say, no, max length, okay, 3. So I need to go to 16 gauge. Gauge is how we determine, unluckily, the cable sizes. And this is the cross section of the cable. And the cross section is of 1.3 millimeter. So when you buy cables, you basically set up by gauges. So this is more or less a semi-thick wire, not that much, but, and you have, yeah, here we can see clearly, 16 is the thinner one, lower the number is the thicker one. So you need to choose your wire according to your voltage and your ampere consumption. Once you have choose the cable, it needs to be the same with the connector. You need a connector that can hold that amount of electricity. Not too much on the voltage, but on the amperes. And you have different type of connectors, and each one is good for different purposes. You have Molex connectors. Molex connectors are usually mostly used in electronics and computers. Is a connector really used in computers, and outputs that doesn't have a really high power consumption. I will say lower than 1 amp of these ones. Outdoor light system. This you can find really custom ones, and we cannot specify. USB cables. The cables are also rated for a certain amount of electricity. For example, USB 2.0 can deliver only 0.5 amperes. USB 3.0 delivers a maximum of 1 output on the USB port. But this is a standard because, for example, you have seen some fast charger, as Daniel was stating, the phone chargers right now, they have what is called a fast charge, or like they don't depend on the manufacturer, they call it a different way. Those ones, they provide a maximum until 3 amps. So the USB 3.0 cable could be rated higher than the standard. That is what actually the phone manufacturers do right now. And for example, I don't know if you have, I don't know, my phone is a OnePlus or Samsung or iPhone. The cables are slightly thicker, and they have usually a fancy color because they are rated for charging at higher amperes. For example, iPhone doesn't embed fast charge on their devices, so the cable is still thinner. If you compare right now an Android cable and an iPhone cable, the iPhone is thinner. I really think it's because of the reasons, because they want to sell you more cables, but and you have cylindrical connectors that you have the jack, you have jacks of different sizes, and you have the power DC plug. Those ones are nice, but they cannot deliver a lot of amperes. A standard 2.5 millimeter DC jack usually can deliver a maximum of 5 amperes constantly without overheating, but depends a lot on the manufacturers. This you need to go one by one and check the manufacturers. You have the good point of this connection. I would say that what you want to always to avoid is this. You see, we have a positive and a negative, and we can connect in any direction. That is something that you want to always avoid. Have the possibility, the impossibility to connect with reverse polarity of your circuit. And you want to have what is called a female connector with a certain shape. For example, DC jacks, not always, because Óscar told me yesterday another completely different thing. Usually outside is the ground and inside is the positive. So the positive is isolated, so you cannot make a short. But,
yeah, but it depends on the actual plug. It's specified that there's a sticker normally that says where the positive and the negative are, and believe me that we have burned quite a few power supplies just by connecting them the opposite way, like connecting a positive on the outside to a negative on the outside, so different ones, and they, of course, you're making a short by inverse polarity. So yeah, this happens, so be careful.
That's why I don't like those connectors too much, but right now it's quite a standard to find them in every household. And you have the Tamiya connectors. Tamiya designed these connectors, I think, in the late 80s, and they're quite good. And you can see one of the connections is round, another one is square. So actually, it's impossible to connect them reversed. is quite good. The problem with this connector is they cannot provide constantly more than 20 amps. So they are meant for low ratings. You have the XL connector, or also called aviation connectors. Those connectors are really industrial and depends basically on the size of this. You have from these ones of like 5 millimeters to 3 centimeters. Will depends on the rating.
I think Bruno knows very well these connectors, right? I don't know if he's online, but these are also used for audio, canon, lighting in theaters and this type of thing.
I think Bruno isn't in the class, but yeah, I use XLR for microphones.
Mm-hmm. Usually these connectors share at the same time data lines and power lines because you can find them until 16 pins. So it's really nice to make really complicated connections. That's why you're using those pins. You have the DSP, that is a lighter version of the Tamiya one, and you have the Keycon, that is usually for example, the 3D printers and power supplies use this one. So actually those ones, they duplicate cables. They don't just use one connector to provide everything, but they have 2 positives and 2 negatives. Why? To avoid overheating in just one small point. Instead of having one point that is really huge, they divide it in 2, so actually they separate the electricity consumption between both, so they have to design smaller connections. If you work onto batteries, this is, for example, another aviation connector. It's quite good. If you go to batteries, the last thing I'm gonna say is you can find batteries connections of, where is this? Sorry, so many links right now. Oh my God. Yeah, bullet connectors, quite standard. Basically, it's a female male. The problem is, as always, you can connect the opposite cables because usually the cables are separated. So that's why the T-DIN exists. Basically, it's a T. One of them is a 90 degrees in respect of each other. But this connector are only rated, I think, until 30, 40 amps. So you have a problem. Usually, the plastic that produces this is not that good. Usually, this kind of high power connectors, the metal is covered in gold to a lower resistance, so they heat up less. And you have the XT connectors. You can find them, and these ones are right now most of the standard for high power driving trains. Is XT30, is half the size and can drive 30 amps. XT60, 60 amps. XT90, 90 amps. XT120, 120 amps. That is it. That is continuous draw. That means, for example, the XT60 connector can draw 60 amps continuously, but can drive, I think, 120 for 10 seconds. This you will go onto different data sheets. So more or less, this is a whole perspective of how to move things. I think Óscar will go now. No?
Yeah, I think probably it's a proper time to take a break, like 5-10 minutes.
Yeah,
at least.
Sounds good.
Okay.
Thank you, Edu.
Thanks, Edu.
Okay, we'll pause the recording.
And it's
okay. So I'm going to share my screen. Just a couple of extra comment about what Edu was saying. Can you see my screen?
Yeah.
Okay. So, oh, this is very annoying. Okay. So one thing, very quickly, well, you already know that I was part of automotive, so I always try to give you some extra tips on how things are done in the automotive world. So this is, for example, in the output of an engine, you have something that is called the flywheel. These are meant for increasing the inertia of the engine because like normal combustion engines have a lot of vibration. And there's just a metal disc that is meant to increase the rotational inertia and reduce vibration. It's like a mechanical accumulator, let's say, and that helps you filter out a little bit these vibrations in the engine. This flywheel is also used to estimate the engine speed by using a Hall sensor, the same as Edu was using earlier. But It also is used to estimate the position of the engine. And engines, modern engines nowadays, have precise electronics. And the newest engines that I work with, before I left, they had a system to counter-rotate the engine to always put it back into the most optimal position once you stop the car. Meaning that when you, for example, are going into a traffic light and you stop the engine will rotate itself without combustion into the most efficient position so that the cranking situation again is fast. And so you can restart the engine again the fastest as possible. And they do that by using this system. So you see that you have the Hall sensor, and basically since the flywheel is metallic, then you can count steps in when the tooth pass next to the Hall sensor. But as you see, there are some teeth that are missing. And this is used for estimating where the position of the flywheel is in. And basically by detecting where you don't have a pulse, then you can see, okay, then my engine is in this position. I can rotate however many degrees back and forth. This is also used because nowadays engines really need a very accurate estimation of where the top dead center is called is positioned. So it means where the piston or the piston head is on the upper end, so that you can inject in the most efficient angle. And this you need to estimate it very accurately. So basically you see that the teeth in the flywheel, you see them here in this image, are very we could say as a gear, but they are normally not meant as a gear. They are just meant for detecting the position of the flywheel and also estimating the motor speed. Another thing that we could talk about, and this is not about engines, it's about PIDs. So this is quite a field, and this is not meant to be like a control theory class. There's like 4 months of classes in university for these things. So this is kind of a complex stuff if you want to master it, but it doesn't mean that we cannot understand how these things are done and start trying with the tools that we have at hand. So imagine that you want to control anything, like for example, the speed of a motor or the position of a drone or the angle of, or the position on a CNC or the inclination angle of a drone, something like that. Most certainly you're gonna be measuring something. That something comes from your sensors, like a tilt sensor or the encoder or the Hall sensor that Edu was explaining earlier for the speed of the motors. And that is basically what you see here on the left side is the RT, is basically your input, what you are measuring. You're going to calculate an error of that input with respect to your what you call a set point. It's basically where you want your input to be. If, for example, let's take the example of the motor. If you want to be running at 9,000 RPM, that's your set point. The actual RPMs that you have, in, let's say 8,500, is the measurement. So you're going to calculate the difference of them both. And then you're going to estimate what we call the error, just the difference, and the difference of the speeds in this case would be 500. Now we're going to put that into what we call our PID. A PID is nothing else than just taking that error and doing different operations with it. The first operation and most simple that you can do is just multiply that error by a constant. And that constant can be something that you make up, like, I don't know, 2, 3, 5, 0.5, etc. Of course, the bigger that error is, the bigger that constant is, the more reactive your system will be. Because at bigger errors, you are responding with higher actions that you have as a of your control system. Then you take that and you make an action on your process, and you see again what the output is. For example, when you are controlling speed, you might increase the current or the voltage on your motor. And by that, you can see what the effect of that increase is on your system, because you have a sensor and it gives you the feedback onto your controller. This basically is what we call either, if you see this line and you forget about this loop on the bottom side, if you don't have that loop, it's called what we call open loop. Basically, we just have a set point and we actuate. If we want to have feedback, and then we close this loop because we have a decision that we are measuring and checking with an error, then we have closed loop. So the different components of a PID are different operations I was saying, and the first one is just multiplying the error by something. But of course, that is very simple because you might have a lot of inertia in your system, and that can lead to either undershoot, meaning that you will never achieve a steady point in your desired output, or that you will overshoot. And for example, you would have like a big oscillation after you have achieved your desired set points, because there's nothing intelligent in this. We are just taking the error and multiplying it by something. And this is like trying to imagine that you wanted to achieve a certain speed with your bicycle, and you were just saying, okay, I have I'm lacking, I have 10 kilometers an hour gap for my target speed, and I want to, and I'm just keep going by multiplying that times 5 times 5 all the time, until when you reach 0, you won't be actuating anything, but you have still a lot of inertia. So you will very likely overshoot unless you do a little bit of braking before you get to the point. So that's why all the other two, the other components are there. The first one is the I, so is the integral component, meaning that since you will very likely have a static error, meaning that you will never achieve a perfect output matching of your system, like the set point and the actual reading will very likely not be the same. You will have a small gap in that, and you can integrate the difference, meaning that you can accumulate the difference of them both and then multiply that by a constant.
Oscar?
Yeah.
Can you put the latest video that I said in the chat maybe while you explain this, because I think it's quite visual.
The chat, more chat. The last video?
Yes.
Okay, yeah, so that's the one that you were saying earlier. So you see, for example, this is only using the proportional part. And you see that you increase, so when he, or I guess it's a he, puts the angle very separated, then you are increasing the error a lot. And that you're basically multiplying that error times a constant. And you see that it goes somewhere close, but that here has a big oscillation. And the biggest oscillation that, the bigger the constant, the bigger the oscillation will be. And you see that sometimes even doesn't get to the steady state point. So that it doesn't get fully vertical and stays with, let's say, what we call a static error. But you see that he's iterating with this, and he's saying that you are that you have a steady state error, and that is quite oscillating. Before we talk about that one, the D in the PID is about the derivative component. So imagine that you take the derivative of the error, so you see how much it changes, and you see that your error is decreasing. Then you know if your error is decreasing, you want to reduce a little bit the action that you're doing so that you don't put that much effort since you are already getting there. And that will help you not overshoot and not go past your desired set point. And that is basically another constant that you multiply times the derivative of your error. And that's what he's trying here. You see that the derivative, so he's trying with both the derivative and the constant, the direct proportion, and that you reduce the oscillations and you reduce the steady state error. And finally, he talks about PI control. You see this. So imagine that we remove the derivative part and that we put a huge error. And you have a huge overshoot. You see this second part that it's like it oscillates past the set point and then tries to compensate very slowly. That is the integral part, because you are accumulating the error over a certain amount of time, and you're compensating over that accumulation. And meaning that if you have a lot of accumulation over time, you will actuate more so that you reduce that. And if you have little accumulation, then you won't actuate. The idea is that you are able to, by calibrating a PID, is basically setting these values, these 3 Ks, the P, the I, and the D, so that you don't have oscillation, that you don't have a steady state error, and that you can achieve your set point as fast as you can. These things are in control theory, like are called overshoot, steady state error, and tau, or the system response, basically. And of course, this is something that it requires a skill, but there are certain things that you can try and guidelines that you can look up into PID calibration guides and these type of things. But of course, also there are libraries that can help you deal with this. So Arduino has a library called the PID. And as well, they have a PID auto-tune library, which is basically what you can use for deriving or making your system test itself and derive these constants for you and try to help you a little bit with this process. Of course, these things are to be taken with care, to use with caution, let's say, because not every autonomous system is perfect. But this auto-tune library is used very well. It's used broadly, and Edu told me earlier that it was used, for example, in the Marvin firmware to the auto level or something like that, no?
Yes, exactly. So tuning PID is something that is tricky. The first time is really, really tricky the first time you do it, because it's difficult to understand exactly what each parameter does. Luckily, we have some algorithm that they auto-tune the PID, and most of the temperature controllers that you can buy, like for power control systems, they have already the equations done on the factory. And actually, but still, you will always need to fine-tune these values. Luckily, this auto-tune PID algorithm makes, like, let's say 90% of the work for us, but still they are not perfect. So if you want to go, you are really picky and you want to have the perfect tune, you will need to still do it manually. But luckily, the auto-tune behaves quite well by default.
Okay. Very quickly, and just to clarify probably something that yesterday was not explained very well because we were a little bit in a rush. Well, first about MOSFETs. I don't know if you have any question about them. Yesterday we were talking about N channel and P channel, and the difference between how you put them and how you control them. Remember that in electronics, you don't have to reinvent the wheel, and there are a lot of things that you can already take inspiration from. And this, for example, is, for example, one circuit that that you can use, for example, to control a high voltage difference with two MOSFETs, one N channel and one P channel, both in chain. So the N channel actually is working as a trigger for the P channel one. And in here you see that we are controlling with very low TTL, let's say, with 3 volts or 5 volts an N channel, but that N channel is modifying a P channel transistor that has the disadvantage that you need a higher voltage range. If you have a very different voltage range than the one that you have in the microcontroller, then you won't be able to close the P channel transistor. So there are examples for this, and always try to look for these things before you try to invent weird combinations or buy other hardware that you might not find in the lab. Maybe there are things already that can help you solve this problem. Finally, as well, I think that this is must be clear already by now with the whole class today. But if you have any questions about PWM, I think this GIF solves all of them. No, I'm kidding. But basically, remember that PWM is nothing fancy. It's just a technique that you use to modulate and create average voltage levels that are not available in your digital discrete levels. Just one thing that we never mentioned yesterday was the duty cycle of the PWM, which basically is how much time you spend on with respect to the time that you spend off. Nothing else than that.
Sorry, I have a question about PWM. I was reading that you can also turn a digital output into a PWM output through software. I don't know if that means through code, at least in the Node MCU.
Yeah, well, the thing is that PWM at the end of the day is nothing than sending pulses on and off very fast. So yeah, you can do that. Of course, you would need to implement either some coding by yourself or use PWM libraries, and that is already implemented. So you can do it. At the end, if you think of it, any digital output and of course here you have to be careful about the speed so the impedance that pin has, meaning that it cannot do it very fast at some point. But you can, if reading the datasheet, use some of the pins to implement PWM by software. Sorry. Basically, it's something called like bit banking, which is not bit banking especially, but it's like sending pulses on and off. And I think, I don't know if Edu, you put just a link in there or something.
Yeah, I just put an Arduino soft PWM library. But yes, you can emulate them, but you have also the problem of the frequency cycles. Like basically the digital pins that are physically enabled for PWM, that means they can do refresh cycles and really high edge frequency. And if the pin is not native to PWM, that means it can do it, but at lower refreshing cycles. So depends on your application, you might not even reach the frequency of the PWM that you might need. So
it always depends if it's a servo or if it's an LED, basically, like both ranges.
Okay, thank you.
And do you always use existing libraries, or do you sometimes implement your own logic?
It depends, but here at the very end, there's a small part talking about practical stuff, and these are some notes from previous years. But there are two things that to take into account. You need to code and you need to wire, let's say, or you need to implement it in hardware. So if you want to code, first thing is to always look for a library or an implementation or an example that already uses this, because it is so the state of the art now in these things and the community developed by the open source Arduino community and stuff is quite broad, and there are many libraries for many things. So first things first is what I want to implement something on an Arduino. I just Google DuckDuckGo or Ecosia. Library Arduino, I don't know, PWM, or library Arduino asynchronous LED, or library Arduino, I don't know, something like that. And then you will find thousands of them. If you don't find a library, then the next step is to go to GitHub and see if there are projects from where you can take snippets of code and see if someone else has done it as well, and you can get inspired by other people's work. Even if it's not an official library, there's a lot of reusable code that you can take from GitHub, and that is always something very useful. And it doesn't need to be even super clean, but it's already something that can start guiding you to how it's actually done for someone that managed to develop the project or similar things that you're doing. And finally, in terms of hardware, there's the same, but well, the Adafruit, SparkFun, Arduino, and all these people have very good documentation. Instructables, mainly Hackaday and GitHub even, there's a lot of open hardware already and that you can get inspiration from. And the most important thing is that SparkFun and Adafruit and many open source projects, they liberate they open their designs. And I don't know, if you were to design a motor driver PCB, here you have, this is, for example, one of the, we didn't talk about this chip yesterday, but here you have the schematics that you can just have a look at them into KiCad or Eagle, whatever you use, and see how the circuitry is done, what are the values of the resistors, what are the values of the capacitors. For example, when I want to design something with an ESP32, I go and check how the HUSA ESP32 in Adafruit. I check their designs and I see how they connected the pins, how they connected the battery charger, the USB, what capacitors they used, and basically it's all, where is it, downloads. So you have here their design. And already here you can see, okay, the USB, they use a CP210 bridge. They didn't use the same one as we use for the FTDI. They use this power system with a MOSFET in there, with a diode. The reset button, we do it with a normal push button. And here, for example, I don't know, they have an auto reset function so that when you program it, they do that, the thing that we do with the slider, they do it automatically with 2 transistors, and this type of things you can already look for documentation in there. And of course, there's always people, geeks like us, that like to talk about these things. And for example, Arduino power supply. I was reading the other day about how is the Arduino Uno power supply implemented, and you know that they have a barrel jack for up to 12 volts and the USB connector, and you can connect both of them and it doesn't matter. The Arduino will automatically pick whichever power supply considers it best. And for example, there are a lot of guys online that explain how to do these things, for example, in or how to understand these things. And in the case of the Arduino, is something that you could, for example, already understand a little bit by reading this guide. With the concepts that we gave you, here you could take a lot of ideas. Actually, I took some ideas for a board that Edu and I are designing for the CNC router that we were talking about.
Yeah, so as you see, like sometimes going through these repos of Adafruit or SparkFun is quite overwhelming. But think that these commercial PCBs they are thought to be like dump-proof. It means if you connect reverse, they will not burn because they have protection diodes. You can connect two power supplies at once. So actually, if you want to fabricate it for your own, you need to like take all the components. You can start taking out like not mandatory things that is just for protecting your board in case of misbehaving or misuse. That is basically what we did with your Arduino. Your Arduino will burn if you connect the battery in the opposite way. But the Fusa or the Trinket will not. So actually, you can take those design as reference, and you will more or less see which ones are the basic and mandatory components and which ones are the accessory.
Exactly. And just the very last comment, and we jump into LEDs and making lights. Here you have this sticker of the power supply. Well, it was here in this article. So in the power supply, you see the barrel connector, the male. Well, it's difficult to know, but this will be the male. And here you see in this sticker how the power is provided. So in this case, it's indicating that the positive is inside, and the negative is on the outside. And that is, as Ed was saying, is the most common way of doing things. But as you know, there are countries that drive on the right side or on the left side, and there are plugs different in every country and these things. So not everyone does the things that could sound logical to us the same way. And have a look at these stickers to see if they are on the opposite side.
For example, I just remember that Ultimaker and what is the other one, MakerBot, they use the same power supplies, the same voltage, the same amperes, but the connectors are reversed. And actually, I know because I burned one motherboard because I bought a power supply for the other one. I didn't check the polarity. And actually, they just made that just because they just want to be able to have compatibility between the brands.
Exactly. Well, so PAD, what is this? This is almost no, I see. Okay. So we talk about light. So LEDs. Well, you already know LEDs. You've been playing with them a lot. We're just gonna give very brief insights about some of the things you have to take into account. LEDs can come in various packages, various forms. They can be like normal LEDs, addressable LEDs. They can have like different colors in one single LED with four legs. Basic things that you have to take into account. LEDs work with DC current. Be careful with the maximum rating that they have. That's why you put the famous resistor that you have to calculate. Basically, and you already know this, but it's more current, more light, and maybe too much current means less burnt. But the most important thing is that now there's a huge trend about what we call addressable LEDs. Addressable LEDs are LEDs that are not as like dumb as this one, but that they have a chip inside, and you can send them data and and control control their color and or intensity by sending them data in a different way that you would send it to these guys. So that's what we normally call like NeoPixels, SW2812, SW2813, 2812B, 2811. All these things more or less are the same. They have different features, they have different frequency, power ratings, and they behave differently when there's an error or things like that. But basically, they're based in this concept that you have in your LED strip, you have three lines. The first, the most obvious ones are ground and power, and the other one is data. And each of these guys has a small chip inside that gets the data and converts it into signal for the channels that it has. It could be an RGB LED or it could be a single channel one. Normally, for the cost, all of them are currently RGB LEDs. And the data that you send to them is transformed into actions for those LEDs. Also, the data is then sent to the next LED in the row, and basically forming a daisy chain strip that you can address because each of them has a different, like a unique address that is defined by their position on the strip. I recommend that you have a look at this guide. NeoPixels is just the brand, like the commercial brand of Adafruit's NeoPixel, but the SW2812. But they have very good recommendations. Basically, the most interesting things here are how to connect them. So normally you want to put a resistor around 500 ohms in your data line so that you don't burn the first LED that you put in the strip in case that you have very long strips. Also, you want to put a capacitor in your power line in parallel. You already know this. This is just mainly for filtering. And of course, take into account that if you have very long LED strips, each of the LEDs roughly at full white consumes around 60 milliamps. Did I say that right? 60 milliamps?
Yes, it's 60 milliamps because
60 milliamps,
the white, there is no white color. There's
Exactly.
RGB,
The
and by switching both three at the same time, you produce the white.
Exactly. So you have to basically, if you imagine that you want to make one of your final projects or an installation that has LED strips inside, you have to take into account where that power is going to come from. And these things start to grow very quickly when you have a lot of LEDs because normally you wouldn't estimate 60 because you wouldn't think that all of the LEDs will be full on with white all the time. You can estimate a little bit down towards that, and a normal rate is between, instead of 60, you could consider 30 or 20 milliamps per LED. But basically, if you have 1 meter LED, 1 meter LED strip with 60 LEDs per meter, that all of a sudden becomes 1 amp. And certainly your Arduino cannot supply that. So you have to think about how you're going to power that. Either you can use LiPo batteries, you can use these 4-cell batteries, or you can use an external power supply. For example, USB 2.0 will be limited, but USB 3 will be okay. And if you use a phone charger, that normally nowadays you can find 2 amp phone chargers at 5 volts very easily, they would be more than okay. But take into account that when you power LEDs with 5 volts, your data line has to be most likely or ideally should be also in the 5 volts range. That doesn't mean that in all the cases you can you need that, but if you're, for example, using an ESP32, if you don't have enough voltage because the voltage drops along the line, you probably will have problems by reaching the end of your circuit or your LED strip because the data got somehow in the limit of what the LEDs can perceive. For that, you can do 2 things. Either you use what we call a level shifter. A level shifter is simply a device that converts logic levels from in this case, from 3 volts to 5 volts. And basically, you tell it, I have this reference which is from 0 to 3.3, and this other one which is from 0 to 5. My signal is oscillating here. I want to oscillate it in here. So you put this level shifter between your microcontroller and the LED strip. Or another option is that some of the Implementations, more expensive implementations have like repeating technique inside of the LED, so each of them is somehow amplifying the signal for the rest. But these, of course, are more expensive and not as common. One thing that you might have noticed, and this is important as well, and it's a very common mistake, is that in the LED strip you have these little arrows, and these little arrows basically tell you where the data is going to. So if you connect the LED strip and you put data on the right-hand side in main screen, then the LEDs won't turn on, probably just the first one, because the data is daisy chained from left to right, not from right to left. And for that, you have a little arrow that is printed on the LED strip. Finally, if you have LED strips that are super long, imagine like 1, 2 meters, 3 meters, the voltage drop in the lines can be quite substantial, let's say, could be quite big. So it's a common technique to put additional voltage power supply points along the strip. So if you see in here, you see that the pads are quite long. This is meant for you to cut the LED strip in that point and still have connectors on both sides. And basically you could wire another power supply in the middle that keeps the voltage for that part of the LED strip. And this is very simple to estimate because you know how many LEDs you have in your strip. More or less, you could think that well, and you know the power consumption, and with a certain power supply, you can provide a certain amount of amps. So you can put different power supplies in parallel, or trying to keep the voltage across the line by putting voltage points in distribution, just by either soldering on top of the strip or opening it and putting a cable that makes like a small unit. Driving or coding for LEDs. It's well, for normal LEDs is very simple. We've already done this in the class. There's not much to talk about. You can either turn them on or off, or use breathing with PWM. If you are using RGB LEDs, you have to think which one, if it's a common anode or a common cathode. I think Benji was having issues with that with one of his designs. It's basically if the current goes, so if you have a common positive or a common negative, and that depends on the design. You can use libraries for addressable LEDs. The recommended ones, I've used NeoPixel or FastLED. Both of them are fine for beginner type, but I think Edu is more keen on the FastLED library. And if you are not using, let's say, addressable LEDs, and you are using normal LEDs, you can use one technique that is called Charlie plexing. That basically is a way of driving a lot of outputs or a lot of LEDs with a fewer amount of pins, so that you don't have to put one dedicated pin for each of the outputs. And you achieve that by combining the different outputs and the values of the resistors here, so that your LEDs can turn on or off by combining 3 output pins. And here we have 6 LEDs. 6 LEDs is, so sorry, we have 3 pins. So 2 to the power of 3 is 8. So 8 is bigger than 6. You can control these 6 LEDs by the combination of these 3 outputs. Of course, if all of them are 0, there won't be any power given in here. So that's reducing 1 already. So you can control up to 7 LEDs with 3 pins. But well, that technique is, just so you know, is called Charlie plexing. And finally, in outputs in general, there's one thing. Well, there's always this idea of what is synchronous or what is asynchronous. For that, one of the good things, let me share my screen with the whiteboard. So you can have your LED strip, your piece of code.
It's not showing the whiteboard.
Sensor. Now?
Yeah.
No.
Okay. Okay. So imagine that you have your Arduino code and you have void setup. Then you have void loop. And in here you say, okay, I have very simple LED on, delay, LED off, delay. This basically is turning on or off your LED all the time by with a delay of 20 milliseconds for each time, right? We already know this, but this is what we call synchronous, meaning that our program goes like this, and then it comes back here, and that's the whole thing again. And it's stopping here, and it's stopping here. And here we really pause the execution. We don't do anything else unless we are waiting for what we call interrupts. That we will see what that is in the future, but it's basically like if we were interrupting our microcontroller with outputs or with inputs, sorry, so that it makes important decisions. For example, like a safety switch or a sensor that goes over a threshold, and that is like priority for the actions of the microcontroller. So this is basically all running like that, and here we are pausing the execution in these two moments, and we won't do anything else. So if we have another function that is triggered or something like that, it will have to wait for this to happen. That is somehow what we would call beginner design, or not like deployable design, because basically it's doing nothing else. But what we want to do is something like this. So we have our voice setup. And then we have our void loop. And then we have our function, let's say, for example, sync function. And here we have LED on, delay, LED off, delay. Okay. So in here, inside our void loop, we don't want to do this on and off thing. What we want to do is call async function starting now until and do it for 10 minutes, something like that. Of course, you won't write this in the Arduino code, but it's just to simplify it. So when you do this, you're going to call this function. You want it to do it in a synchronous way so that it doesn't stop what you're doing. And after this, then you will be able to do something else. So let me just expand this. So you call the function, and then you what am I writing? Do something else in here. So the idea is that when your loop is running, you just schedule something. You say, okay, I want you to do this operation for 10 minutes all the time, but I don't want you to stop the other things that I'm doing, because very likely my system is not only going to have that, it's going to have more things. Well, then I can call this asynchronous function and do other things in the meantime. How do you implement these things? Of course, this is not something easy. You can do it in most of the microcontrollers, but of course there are libraries for that, and one of them is called JLED. JLED is what we call non-blocking LED controlling or LED control, which allows you to do this type of things. And if you look at the code, and this is one example, basically what you're doing is I want to use a LED that I have in pin number 9. I want to breathe during 1.5 seconds. So a breathing time of 1.5 seconds, do it 6 times, and start after 5 milliseconds after each run. And then I just say, do it, and that's it. Then this will take care of the execution, and you don't have to pause your own, like how your code is running to take care of your LEDs. This will basically just run that in the background somehow. It's like the background processes that you have in your computer, that every time that something happens in the background, you don't have to pay attention to it, and your whole computer doesn't halt. The same way with this. Here, if you have a look at this library, is well, I've used it even for like art installations in the past, and it's very useful for you to, for example, program outputs with not only non-blocking things, but with more complex effects. Like I want an LED to be on and off forever with a certain frequency, and that I can also modify that with when I, for example, type into a keyboard, for example, and then the thing automatically updates itself, and the LED is blinking in a new way, but I don't have to touch the whole code for doing that. And I don't have to touch delays. I don't have to touch. I don't have to stop the execution or anything like that.
Oscar, sorry. So that's basically the same thing that you do with when you're coding with millis instead of delays.
More or less, but the thing is that this thing takes care about. So millis, it gives you the time that has been that has the elapsed time since you started since you powered your Arduino. So if, for example, it was like 5 minutes, it's whatever amount of time in milliseconds since you started the Arduino. So 50, so 5 times 60 times 1,000, 300,000 seconds. And then if you program with millis, you could say, okay, I want that every time that millis is a multiple of 10 to do something. That could be, but then it means that you have to do a lot of conditions already by yourself and program quite a big structure of code to do this type of operations. But more or less, is something like that. The only thing is that so that doesn't grow endlessly, then you can have this implementation. And the nice thing as well is that this doesn't have to be LEDs. When I did this art installation, I was running like lamps, like 230 volt lamps, normal lamps. And when I was triggering were solid state relays, not LEDs. Basically, at the end of the day, a solid state relay or a relay in general can be can receive 5 volts or 0 or ground or 0, and the same way the LED. So this is not only for just turning blinking LEDs, but also for relays, for other actuators and things like that.
But
what else?
The libraries help you to operate tasks in parallel, or just to simulate the parallel effect and put it in series?
Yeah, exactly. So basically, you program things and you say, okay, I want you to do this somehow in the background, in another, let's say, in a non-blocking way. And when you, so you see that you have the small delay when you turn on or off the LED. The idea is that when that delay happens, you are not blocking the whole program. So that is taken care by itself, but you don't stop and you don't waste, let's say, your clock or your CPU speed by stopping or pausing the execution.
But at the end, the CPU can only deal with one task at a time, right? It just
simulates
the effect. Okay.
Exactly, it simulates effect. But also, I mean, threading in Arduino it can be done, and there are multi-processes implementation for that. But this is not a threading algorithm. This is just asynchronous.
Thanks.
Okay. The very last thing about lights and stuff is something that we call L wire, or we call it electroluminescent wire. What is that? Is you seeing my screen or you seeing my whiteboard still?
Yeah, I think you need to switch from the whiteboard.
And no, you see nothing. You see my. God, this is slow. You see my screen back again?
Yeah.
Okay. So the last thing is what we call electroluminescent wire. This is something like LEDs, but not the same. Basically, what you have in here is several layers of PVC, and inside of a conductor that is coated with phosphor. And phosphor is a luminescent material that when electricity hits it, then it will emit light. And when you put electricity through these guys, then they emit light. And depending on the color of the coating that you put on the outside, then you will have different colors. The nice thing about these things is that they consume much lower power than LEDs. They are not addressable. So the whole thing is just lights up and that's it. But you can have several of them in parallel and control them with different coatings or colors. They light up the whole thing, and the nice thing about them is that they are flexible. So LED strips, for example, you have a limited bend angle or flexibility that you can have, or you have to cut them and then solder wires. But these things are quite flexible, as you see here, and you can basically power them or control, like turn them on or off. But the one thing important thing is that this is not DC. These are run with AC, and for that you need either what we call an inverter. An inverter is electronic equipment that simulates AC current, and you can find them online, like for 12 volts, 3 volts, 5 volts. It depends on your electroluminescent wire configuration. But remember that these are not to be run with DC. This won't work basically with DC. They need alternating current. The nice thing then is that you can either power your inverter with a battery and control your inverter on and off if you want with an Arduino. But they cannot be connected directly to the thing. I think that's it. I don't know if
are they bright enough to do anything useful, or they're just pretty?
Those you know, like the suits on the sci-fi movies. Nowadays, everything like done with CGI, but
yeah, I thought it looks like some Tron stuff, you know.
Exactly. It's done with this kind of wires.
Because I wanted to do a little lamp for some project, but I don't think it's bright enough to be able to read, no? Or except if you can like roll meters together.
They self-light, but they don't provide so much surrounding light.
Yeah, the thing about them is that, well, they're nice in darkness, but also you can see them in different shapes. So not only like a wire, but also like a panel or like a tape. For example, this is like, I don't know, when you go to concerts or things like that, they are not the same because they have power, but these wristbands that you put in concerts, and there are different formats. For example, when you see these light suits, some of them use the panels to put something on the chest, or like these things on the
like on the parade, Disney.
Yeah, exactly. So these are like quite common for this. So if you want to be like a geeky guy with one of these suits, you can make them with L wire. But as you see here, the thing is, well, the nice thing is that they are quite flexible. You see here that you can have very intricate forms. But if you want to see them at plain light, they're not going to emit that much light, basically because they are like they're based on phosphorescence and not in like photoluminescence like LEDs.
Another bad point of this CL wire, let's say, is in the long-term run, let's say 1-2 years, they get lower and lower phosphorescence.
And what's the consumption power?
Ridiculous.
Yeah, it's
like
super low consumption.
Some small pocket inverters that you to put on your clothes, like the run of some coin cell batteries.
Okay.
So it's really minimal.
And the amount of current define the brightness, or it's just on and off?
It's on and off.
Oh, okay.
And the very last thing before we go to DIY outputs are, so we talked about motion, we talked about lights, and now we're going to talk about sound. So making sound in with Arduino is also, well, with these outputs is also possible, but don't expect magic. This is not like speakers or things like that. This is just, these are buzzers. Buzzers basically have this thing inside. Basically is a small ceramic plate that has a piezo element inside. A piezoelectric material is a material that expands or change size when you put it with electricity. And basically by putting high frequency on that piezo material, it will expand and contract, and that will resonate inside a ceramic material, and that will generate vibration on the air, surrounding air, and that's what you perceive as a tone. Things that you can do with this, well, as I said, they're quite limited, but you can have buzzers, and with just 2 cables, you can make simple tones. There's a library for Arduino called Magically Tone that helps you just send a PWM onto that buzzer just with by defining the frequency and the pin that you want. And if you want to be to going into more interesting stuff, like for example amplification and making actual sound, you have making actual music, you have to talk about DAC circuit, which is basically a DAC is what we do with an ADC, but on the reverse. So basically you generate analog signals with by inputting digital ones. Of course, this is going into signal into the signal field, and this is kind of a complex stuff. But of course, there are boards that you can find for this. You can do it either with Arduino or with Raspberry Pi. For example, in a Raspberry Pi DAC shield, you can have shields that improve the sound quality that gets out of your Raspberry Pi. For example, this one, which basically is generating a better audio quality for your speakers. But always keep in mind that sound and speakers, they have certain levels and that they need to be very likely amplified. Means amplification is the process of making a small signal or a weak signal, turning it into something more powerful, but in the meantime, not putting extra noise. And that's where the money goes to. In complex sounds and high fidelity systems, the money goes into not only amplifying, but also removing the noise in your sound system, and as well into the DAC part, so that you can have a better depth in your sound, meaning that you can capture more different granularity in your different tones of your sound. Now, that of course, you are talking about more higher prices. This is not like 2 or 1 euros. This is like 30, 60 bucks. But of course, you can get into those things. If you want to learn a little bit what these things, I lost the page. What these things are, not only the DAC, but also amplifiers as, where the hell did it go? Also amplifiers, you can learn about amplifiers and you can use amplifiers with transistors, as Andrea was saying yesterday. And that is here, amplification. So here you have different configurations of how to use an amplifier or how to make an amplifier with just BJTs or transistors. And here is a normal, probably one of the most common amplification systems. Basically, you have a small power supply. This is your signal that you're generating either with your sound system from a DAC, or you could try with PWM, but it's going to sound very awfully. And basically, you have your high-end power, your high-end voltage that you are providing to the amplifier. And with a transistor, you are using this, what we call voltage divider, basically two resistors in series that divide voltage because of simply Ohm's law and the ratio of the resistance that you have in here. You can turn on and off this transistor in here, and based on your input, and output that to your actual speaker in a higher range. Of course, it will depend on the voltage, on the voltage levels that you have in your input and the desired output that you want, so that you have and that will define, the values for your resistors in here, and more importantly, the ratio between them, and also the orders of magnitude. And you see here that we are starting to see also capacitors in the line, so that you can remove a little bit the noise that you will very likely put while you're doing this process. Well, that's especially because when you have high frequencies in sound, then these transistors don't open and close exactly how you want them. They take a little time. There are overlaps in the signals. These resistors and these power supplies are not exactly perfect, and they have a little bit of oscillation in the voltage. And basically, you want to take care of all these things. Just one thing and one advice, if you're looking into doing more complex things with sound, not only with buzzers, is that try to match the specifications of your speakers. Speakers have what's called impedance. It's like let's say the value, the internal impedance of the speaker, and you have to match this with your DAC configuration. You can configure speakers in series, in parallel, and however you want them, but you have to be careful so that you don't burn your DAC or you don't destroy your speakers. Basically, you are making them oscillate too much, and at the end, the speaker is just let's say a combination of like a resistance and inductance and capacity. And if you oscillate, over oscillate, or you under oscillate, then your sound quality won't be good. So try to read about how to match the specifications of your speaker with the specifications of your DAC. It is not the same to put, for example, a 10 ohm speaker with like a normal DAC than to put a 2 ohm speaker, and normally is specified in the bottom part of the casing of the thing. Here, different configurations about amplifiers. Basically, well, you can use transistors, but again, when you're dealing with high frequencies and these things, so every time that we see a color changing from green to red, means that there's a joint in there. And when you have waves and signals, very likely it's like water in the swimming pool. When you have water in the swimming pool and it hits the edge of the pool, it gets reflected. So this is the same. There's a change in the mean, let's say, in the means of transmission, and there's a little bit of reflection in there. So you have to be very careful with your joints, with your the solder that you put, how clean your system is, how long the lines are, and etc. Especially if you're dealing with either microphones or speakers, you should use isolated shield or shielded wires so that you don't have interference on your cables, and you don't create interference from your cables outside to the speakers or other electronic components. And here is like, again, this could be 5 years of university degrees or special, like specialized people, but of course, like get into what you think that these things are more interesting for you. And the last thing we already touched on a little bit earlier, before we jump into outputs and do-it-yourself outputs. We talked a little bit about practical stuff, so how to wire for an output, how to code for an output. We already talked a little bit about that earlier. But an important thing also here is to talk about debugging. So just some very
Óscar, sorry. Maybe before you go to that part, can I ask about how good are piezoelectric materials to generate energy, and what does it depends of the size of the material, or even the material, or?
So to generate energy, sorry. So you put mechanical effort, let's say, and you generate electricity out of that. It was a question.
Yeah, no.
Okay.
I was. How do they work? I suppose, or what I have understood is that they work like backwards of how a speaker works. So it's the electricity making it pump, but when you pump, you make electricity.
Yeah. So you got the thing is piezoelectric materials, like for example, quartz is one of them. And they are used in like for small things like a watch, and that, for example, you have seen probably in the past watches that just by wearing them, and when you shake them, they get a little bit of energy and they get recharged. And also, for example, for giving the pulses for the mechanism in the watch, the piezoelectric material or the quartz is used in that sense. But as you see, I'm only talking about very small devices, and I'm not an expert in here, but the thing is that the electricity or the pulses that you generate are very, very, very low. So we will be talking into the millivolts or like nano or milliamps levels, probably even in the nanoamps level. So just by putting pressure onto them, you could generate some pulses, but again, it's pulses and not a constant source. And secondly, the levels are very, very small. So you could use them for very small things, like, I don't know, driving the mechanism of a watch.
And could you save the energy you produce with a piezoelectric material during the day in a, I don't know, a capacitor or a sort of battery or something?
No, I mean the energy capacity that those things have is like think about storing it into a rock is really inefficient. It's like it could be in the lowest level of Edu's chart, even lower than acid batteries.
Thank you.
Of course. I mean, and you would need like a building to even be able to store a little bit of, and maybe. Well, and the thing about this is that when you put pressure into them, so that the thing is that piezo is, I don't know if it's Latin or Greek or whatever, I don't know, but it's like you put pressure onto the material and that generates a little bit of electricity. And the other way around, you put electricity and it expands or contracts. Is the way the material reacts to pressure, let's say. But that is like a transitional state. If you compress it, it doesn't mean that it's going to save electricity in the material. It means that it's going to generate a pulse, and that pulse very likely will be dissipated through ground or something like that, unless the material is fully isolated. But it will very likely just dissipate into static electricity or things like that, and you won't be able to recuperate anything out of it. But as a concept, is cool. But no, it doesn't work luckily that way. One thing that you could do, and if we want to talk about storing energy, how is this? Yeah, is what we what they call gravity storage. So imagine that at the end of, you know that when you hold something here, you're putting energy on it because the thing tends to drop, right? So you put if you don't hold it, or you reduce, or you don't put energy into the pen that I'm holding at the moment, it will just go down. So the same applies for large scale, and like imagine that you could build a concrete block that is like the size of that, and you could pump water under it with huge pumps, and basically you could modify the height of that concrete block, and by that store energy. When you don't have pressure underneath, then that block will go down and power a turbine. And when you want to accumulate energy, you put electricity under it, and you store energy by lifting the block, the whole thing. And that is like battery, like a high, like large, super large scale battery. But instead of using electricity, chemistry principles, you're using just gravity. Other people have been doing this in the past, but instead of using that huge blocks, you could do this.
I thought about this, about using, for example, solar panels to pump water up, so that whenever there's sun, it's always storing energy through pumping water.
Yeah, that is something that is already done in many water
deposits.
Water deposits, exactly. So if you have a deposit up the mountain and a turbine under it, you can reverse or pump the water back up, and that way you're storing energy. Of course, everything has efficiency, and the efficiency of the process, you lose energy in the meantime while you're pumping water up because of your pumps, because of friction, etc. But that's a way. And also there are projects also for storing energy, not only with a huge tank, but with small blocks that you can move with cranes, and you just basically pile them up and make huge towers of individual blocks that you recuperate the energy when the blocks go down in free fall, and that makes a generator turn and generate electricity back. But again, these are like mostly conceptual. And here, for example, this is a small image of what you were saying, Benji. Where was I? Here. So talking about designing your system, debugging, and these things. Three things. The first one is divide and conquer. Don't try to make something from the very beginning that is huge, that has a lot of mod, that has a lot of parts, and that tries to cope with all your problems at the same time. Try to go step by step with small things, and try to make modules that can then talk to each other. Be methodical. Try to not do things like this when you're prototyping, but prototype like this, because this is, you take a picture and you already know what's going on, but here is impossible. So try to be somehow clean. And also use the tools that you have at hand. So for example, use the multimeters. Before plugging in things, especially now that you're gonna be handling larger voltages, not 5 volts from your Arduino, but voltages and amperage that could hurt you. Check with a multimeter before plugging things into the power supply. Always keep in mind that ground has to be connected across your whole thing. So if you have a 12 volt power supply and an electronics that is working at 5 volts, the ground has to be shared at some point, either with the ground that you have on your house, or something similar. But a common mistake is, for example, that you're running LED strips with an independent power supply or with a battery, and you are powering your Arduino without the power supply connected from your computer. And then all of a sudden you're managing different voltage levels, and probably you have a static electricity on your LED strip, or your computer is statically charged, and that ground is a little bit higher and your LED doesn't work. So try to, for example, reduce noise or reduce these things, but always keeping in mind that the different areas of your circuit have to have the grounds connected. Be careful with heat, especially when controlling and cutting energy with switches, heat relays, MOSFETs, drivers. These things are hot, and you might need either radiators or fans to evacuate the heat. And all these things require a lot of expertise, so don't hesitate to ask or look for information, especially when you're designing your own PCBs, because if you design your own and you don't evacuate the heat, for example, from a MOSFET, very likely your PCB will burn, or your solder will come off, or your traces will degrade faster, and this type of things. So heat is something very important to care about. Yeah.
Yeah, since you are talking about that, I was about to ask, like, if we can have like a session to debug. For example, I am designing something, my circuit for my final project, for example, and it has many input and output stuff. And so I don't want to go too far before being reviewed. I mean,
of course.
If we can...
So we haven't planned this thing specifically. So the best, I think, is that we plan a session, and that is not something just one-to-one, but more a session in which anyone is free to connect. And for example, you tell us about your progress and what have you been doing, and then we try to debug it collectively, of course, with no compromise for the rest. But we try to do this in a session together. And I don't know what you the time slot that we can allocate for this, but I think that one of the days in the afternoon or something would be fine.
Yes.
Right. Yeah.
And yeah, I mean, some other things. And just the last thing I say, and I let Edu go for the do-it-yourself outputs, is when you're doing coding for these things, your code will start to grow from 50 lines of code to 500 lines of code very easily. So when you put a motor in your machine, or you put an LED with a special animation, don't go and put the code of your motor on the working sketch that you already have, or your working script that you already have. Try to just drive that independently, make sure that it works. And once that works, then put it in your whole system, because very likely you're going to have a lot of things that are clashing. And if you try to debug 5 problems at the same time, it's going to be very tricky. But if you isolate problems, and just by doing a small sketch of your of the system that you're working on, for example, just running a DC motor, for example, with a MOSFET, and you make that work, then you can put that chunk of code or that piece of hardware into your whole project. But don't try to put that into your whole project from the beginning, because you're going to run into 10 problems when, for example, only one comes from the actual sketch in there. Use serial prints, comments for debugging, and all these things. Structure your code in functions. Try to make your code that is not monolithic, like a huge blob of void loop, but try to structure your codes in functions, so that especially when you repeat things or actions, you can reuse pieces of code and make it as intuitive as possible. Why? Because when you, very likely you will ask us to have a look at the problem in your code when things get more complicated. And it's very difficult to read someone else's code, as you know. And if you structure things in an intuitive way, and you say, I don't know, a function for making an animation for LEDs is called LED animation, then it's very easy to understand. But if the function is called my function, then I don't know what's going on. So it's like, try to make these things somehow to others to understand. And is and this is just the last sentence. Do not hesitate to ask. I mean, many times when I've been doing coding, I'm coding with two people. Like I write code and someone else checks what I'm writing, or someone else writes and I check what they write. Because when you do these things, it's very likely that you won't see errors and you get so into it that you don't see it. And something is very stupid, but don't be ashamed to ask. So these days we're not getting many questions from you. And I don't want that to be because you are ashamed of asking. But I want that to be because you are so good that you don't need to ask, but not because you are hesitating. Okay. With that, I let Edu, I don't know if you want to take a break, but if not, I let Edu just go to the next part.
It's gonna be short, more or less.
Okay, so then I stop sharing.
Okay, so before we jump onto the web outputs, let me put your windows in green big. Okay, I want to warn you again about the peligrosity or the dangerousness of batteries. It's not a kid's game. I'm not kidding. You can really easily burn your house on fire. They have some fab labs that have burned on fire completely already because of these kind of things. So for example, this is a battery that just got a hit by a rock, like on the side, didn't got a direct hit, but make a small micro hole, and literally the LiPo run on fire. Just to give you a warning about how to charge batteries or discharge, or especially charge and discharge, you never, ever want to leave a charging battery, especially a LiPo or a Leon battery, unattended. It means don't charge your battery and leave home and go take a beer. Always stay like in the same space, so you can always disconnect the batteries. This is something that usually happens when you're charging. For example, this battery, we're charging and started conflating because it failed, had a mechanical failure. And this is the kind of explosion. First, it makes a little bit of smoke. And this is kind of the explosion that it makes. And this is a really, really small battery. This is the size, more or less like a double phone battery. Not really huge. If you want to store LiPos, always try to buy these kind of LiPo bags that they are metallic and they're closed. Also, like the cookie cans, like the metallic cookie cans, work really well. But for example, even so, just to give you the idea of the amount of power that these LiPos can handle, inside there is like three big drum batteries, like the kind of DJI, like the white drones that are really famous. This is a metallic bag with shields, and it's interior is fireproof. So you never leave a battery unattended when it's charging, okay? And Benji asked before, what happened if you put your battery into water? I was just looking for the videos on it. So this guy was charging the batteries and had the brilliant idea that the battery was going to explode and put in a water bucket. So actually the bucket starts floating. And the problem got even worse. Okay, more questions that you were asking about. Size of these inverters for the EL wires. For example, this is a coin cell inverter. The datasheet states that more or less you can run 3 hours, half meter of EL wire. And this is really, really small, as you see. They have different types, for example, for handling 4 AA batteries. And I think this one can handle like 4 meters for 7 hours. So the power consumption of this actually is really small. Actually, we can calculate the power consumption.
Yeah, what's the actual numbers? Because very small isn't exactly the answer.
Yes, okay. So these AA batteries usually are rated between 1,500 milliamps to 1,800. So actually, if you are running for 7 hours. Okay. First, we need to divide because it says 4 meters between
there's
sorry.
4 batteries as well, no?
Yeah, but this is to just augment the voltage.
Yeah. 6.
They are in series, not in parallel. That's different.
Yeah, 6 volts, I see.
So you divide it by 4. Actually, this is for 7 hours. And this is by 7 hours. So actually, you got 65 milliamps of power consumption of one ALE strip.
Which is like the equivalent of the 1 LED NeoPixel.
More or less, yes. Exactly. It's quite low compared to LEDs. Yeah. Actually, this, to get the proper calculation, you will need to go for the inverter watts consumption, and after just make the equation, because the inverter translates to AC and the power management is different. But to be able to have a scaling of the batteries, it's more or less 64 milliamps. Okay, so DIY actuators. This is hacking class more than actuators, because making actuators work is not that easy. For example, we can make acoustic mini levitators, and these you can actually use ultrasonic sensors, because ultrasonic sensors, what it is actually is they are speakers, and you use one speaker for sensing and one speaker for producing sound. What happens is they produce it in the barrier of the ultrasound that is high frequency. So, of course, the amount of sound power and the sound thrust that it can produce is really, really small. So you can solder just the small speakers. And what you need to do is use, for example, a MOSFET for each one of them. Or you can use other type of chips, for example, the L2930, that is a really, really common chip in the Arduino kits, that basically is a H-bridge chip that is almost in every Arduino kit and is one of the cheapest ones. In case you don't have one of these, you can just wire two MOSFETs in parallel and connect it to the speakers, to each one of them. So as Óscar was saying, the Arduinos cannot make HC sound. They can only make 8-bit, but what we want to do is not produce quality sound. And actually, in this case, it's not sound that we can hear. It's another wavelength that humans cannot hear. So we want to work it with frequencies. And if you want by oscillating frequencies, you can reproduce and make one wave produced by one speaker counteract the other one on the other speaker. And actually, you can make the accomplation of the wavelength just in the middle of the points. So whatever you will put in between will be hanging in the air. So for that, whatever you put, usually you can put a small foam ball between the two ultrasonic speakers. You cannot put with a piece of paper. You need to put it with kind of a small grid, so the sound can also penetrate through it meanwhile you're connecting your foam ball. This is, let's say, it's no more than DIY output, is DIY cool experiments on actuation things. And this is really a really simple one. It's just with two of them. If you just Google a little bit, you can find that people use 30 or 40 of these ones to create like balls in a ball shape. So actually they can hold much more particles in between.
There's also, I don't know if you've seen the Ultra Haptic or something, which is now part of the Leap Motion thing, which is like a sensor for your hands. It uses air to press air on your hands, so you can have a haptic feedback of stuff you do.
No, I haven't seen that.
I'll send the link in the chat.
That looks cool, actually. After having the big session motor class, actually this is a little bit ridiculous because it's just going back forward, really, like 50 years in the concept of motors, like more, not even 50 years, it's like 2 centuries. But Armand was stating that it could not make the motor be driven, no?
I did it, but I guess I did a mistake. It was a short inside the coil. That's why it didn't work. So it was just going back to like.
It's really important that actually you turn the maximum amount of times. Actually, that increases the resistance of the cable, the ideal for making these kind of devices is actually to use the thinnest cable as you can. So you actually spike up the resistance and you turn as much as possible. So actually you augment the total length of the cable and by so augmenting the resistance.
But if you do it like super like heavy, it's gonna be super heavy. It's not gonna turn.
Exactly.
So,
it's not gonna turn. It needs to be really the thinnest wire that you can find.
Yeah, exactly.
Also, this kind of DIY motor has a problem. Can you see what is the problem? Any of you? Okay.
You have to launch it by
Maybe
itself.
because you only have one magnet and usually you have at least two of them. So if it stays in a
No, actually the problem is motors, DC motors work by changing the polarity on the coil. And in this case, we are not changing the polarity. So actually this motor is tend to work a little bit, but not endlessly. Why? Because if we connect, let's say this is positive, I think, positive, and we are producing a wavelength, a magnetic field in this direction, one side will be negative and one side will be attracting to the north pole of the magnet. So that means this coil will rotate to match the magnet position, but it will not bounce it back because we are not changing the polarity. So that means if you impulse with your hand, you will be able to actually spin a little bit because attraction and the inertia of the coil will make it make the second turn. But at the end, it will just slowly slow down and stop. For that, you will need to actually design it slightly different with a little twist and put another clip here negative, so actually the coil can change the polarity. Or you can do it by yourself and change the cables really fast. This is a simple sketch on motors and transistors, and for example, how to wire a coil around, how to use any cylindrical object. And actually here, I did some tests, and you can see, you will see a lot of sparks. Why? Because I was using, first, a really thick cable. I didn't have more cable. First, it has not many turns. So actually, I was not using the small battery that is inside. I was using a 5-ampere battery at 14 volts that is able to deliver like 100 amps. So actually, it was making really big shorts. That's because the cable is not good enough and the design was not good enough too. But if you don't make the good design, you can always pump the electricity up and it will still work.
Can you explain how you inverse the polarity again? I didn't understand.
No, in this case, I didn't inverse the polarity. For example, in this case, you see, there has a lot of problems to start, and I'm connecting the electricity. Let's see. You see, now I'm pushing, sorry. I'm connecting in this point, but it's not moving anymore. Why? Because when you connect in one polarity without changing, this becomes negative and this becomes positive, let's say. So this gets attracted. So the only way to start is when actually the coil is reversed. And by having the coil reversed, it has inertia. And even if it is attracted, it doesn't attract enough to stop it. So it will go down, but it slowly will start grabbing and slowing down the speed of the rotor. For that, actually, this example is much better because it changes the polarity automatically. Why? Because it's a magnet. So magnet has a defined polarity in one side and the other side. And we have a battery connected, and we are making the connection on the other side. So by so, we are touching the part of the magnet that has negative. And we will connect, we create a circuit that make it twist, and when it rotates, half of it, we actually connect to the other pole. So we are all the time bouncing bound automatically using the magnetic properties of the magnet itself. So we change the poles by rotating the magnet. And actually, it's cool and it works really fast in theory. Unless you don't get a proper magnet and doesn't attach really well. But theoretically, this circuit is much more efficient and you don't have the problems of stating up of polarity change. Actually, you can keep it continuous until you don't burn. For example, how to make, yes?
Sorry, so if you put basically a magnet in that coil, then it would be analog to this, no?
You mean magnet in here?
Yeah.
Yeah, but you have the problem that you have just one big magnet. So it's a continuous circuit. It has no resistance, and that will make a short automatically in any kind of battery.
Okay.
Other options, for example, we have seen the buzzers, like the Óscar was explaining. Actually, a buzzer is the same as a solenoid. That is the same as almost as a relay. It's the same concept. It's a coil with a metal piece inside. You can easily make it by wrapping around. Actually, this, if you wrap around enough coil and you conduct electricity to the coil, this will move the battery up and down. That is just a DIY solenoid. Another point is to use a piezo. A piezo is used to produce sound, but also to sense. How you can produce more bumps, actually the displacement between the layers, just with a transistor. And the last but not least is, for example, how to make a magnetic stirrer. If you have a motor that is a fan motor that you can find everywhere, you can, for example, put two magnets on the surface and put a little piece of metal inside your coffee mug and magnetic sticks on coffee. There you see. And the last part that some of you might, I think this is the most interesting part actually, is how to what is the difference between a servo and a continuous rotation servo. What is a continuous rotation servo?
One that continuously rotates.
Oh my God. A continuous rotation servo, I don't know why I asked. Continuous rotation servo is a DC with gears. That's all. Because actually a servo is a DC motor with gears that we have an encoder, a potentiometer, and some control system. But a continuous servo is one that we can rotate continuously. That means we don't have positions. So that means it's a servo that we have taken out the potentiometer and the control system. So why you have to do this? Sometimes you want to use a really small DC motor with gears to have more torque, and or simply you want to have a slow movement. And these motors are like micro DC motors with gears, but in a cheap and easy to find package. So it's really common to actually transform it into a continuous rotation movement. When you disassemble a servo, these motors not only have the gears, but they have mechanical ends. I don't know if you have tried to move a servo by hand, but you cannot move it more than a certain position because have some locking mechanism that some gears have a lock point, and usually it's the big gear. So you open the servo, they usually have 4 screws on the bottom, and take out the first gear and basically just cut with a cutter knife the internal blocking gears. Another thing that you have to do, this is how it looks inside. You have the small motor, and this is the potentiometer. Most people, what they do is take out the whole gears and disconnect the potentiometer. I personally don't like to do that. What I do is open up on the back. I don't know why I didn't save that picture. Servo continuous hack. You prefer to usually open the servo on the back and actually break the connections of the potentiometer. That works usually in a much better way. Because by breaking up the connections of the potentiometer will make the board think that you're always in one steady position and will always be targeting for the PWM pulse that you are sending to.
Like deactivating a bomb.
Sorry?
It's like deactivating a bomb.
More or less. But actually, this is how actually the control board inside looks like, and you have like the motor one and the potentiometer that has 3 wires, and in this case they already disassembled them. Some cases depends really on the servo, you will need to put 1 or 2 resistors to actually choose a specific resistance on the potentiometer. So not always just cutting the potentiometer cables work, but you need to jump with usually it's a 1 ohm resistor or 3 ohms resistors. And more or less, this is another one that if you have a Roomba, that is something that I discovered. If you cannot make your outputs, but you have a Roomba, Roomba could be your output. Roomba has a port that actually is a standard FTDI serial port that you can use with a standard 80 commands, the same as the Bluetooth, to actually control it. And actually, there is a few tutorials online, and there is one even how to control a Roomba with Grasshopper with OpenCV. I just think that is quite funny, and I just love it to put it in here because I could not resist it. Like how to control a robot just by sending 80 commands of move 10 meters, move 3 meters this motor, and actually you can deactivate and activate the different tools of the Roomba and even play tones, like music tones with it. An electric generator, this actually is the last one, is let's say the 3 types of how to make a motor. First, you move the coil. Second, you move the magnet. And what happens if you move the magnet around a coil? Actually, this is a coil. Just wrap it around, connected to an LED, the end of the wires. And just by moving the magnet, will actually light the LED because it will change the polarity on how the circuit, if you change, this will attract the electrons here, but if you flip it around, they will move it here. So by that, it will make inductance and produce the electricity on the cable.
And what stops it from turning the other way, like turning back from the way it came, like an AC current? What makes it continue turning?
Sorry, you mean changing all the time the polarity?
Yeah, if you change the magnet, why would the electrons continue in a circle rather than coming back from where they come from, for example?
This actually is a good question. I don't know how to answer it.
Okay.
Óscar. I think I have to be honest.
I think it's just the
inertia,
what is the question?
Why do the electrons, if you have like the magnet, they come to one end, then you turn the magnet so they go to the other end. Why do they continue in a circle rather than like going this way and then coming back and then going like this, like an AC current rather than a DC?
Oh, but the electricity that you put into the coil it always goes in the same direction.
No, Óscar, it's talking about this case, for example. This is an electric generator. It's a coil wrapping around, and it finishes up with LED. It means if we rotate the magnet at the opposite, the electrons will go this direction. But if rotate it back, why they continue this direction and not bounce back?
I think it's because of the orientation of how electrical charge changes into magnetic field and back, and which direction one goes when it transforms.
I think you're right. Magnet. It's the rule of thumb also. Magnetic induction.
So you are looking for Lenz. You're looking for Lenz law. Is this thing?
Which?
Lenz. L-E-N-Z.
En el castellano, por favor, se me da la letra en inglés.
L-E-N-Z.
L-E-N-Z. Yeah, this. You mean, no?
Mm-hmm.
Yeah, I think it's about this concept.
So no, it's also about you see the hand in the bottom, the magnet, motion, and current. That is like what they call the right-hand law, let's say, which is basically your thumb points to the motion direction, the magnet with your pointy finger, and I don't know, middle finger to the current direction. But to be honest, I don't know. I don't have a short answer for. I would have to have a look at it.
Cool. Well, sorry to interrupt.
No, actually, that's it. There is no more class on the way outputs. It's much more difficult to manage actuators than inputs. That's it for today. Well, last thing, and I want to show you that I almost forget about. We have seen that sometimes might seem a little bit difficult to make devices and make driver powertrains. I want to emphasize the importance of proper cooling of the electronics and proper size design. This case, this is an example of something I did a few years ago. Basically, well, we did this intervention. There was a small pavilion and it has like, if I remember well, it was 200 meters of LED stripe, all at 12 volts. And each stripe was at the same time RGB with independent channels. So we could control it at night and have like each section have individual control. Actually, you see the different colors, slightly different colors on the stripes. It's obviously because this was the control box. Actually, the wire length, just because of budget issues, we have to keep the same gauge diameter for all the cables. But obviously, the resistance on the cables to the last one and to the first one was completely different. So actually, this is, for example, how it influences just the gauge of the cable on the different colors of an RGB stripe, and because of the wire resistance. And it is, if I remember well, it was around 10 meters, 12 meters. All the control boards for this were done in a fab lab. Actually, this is a control box, and you can see there was a lot of power. So we had 4 power supplies of 60 amps each one at 12 volts. And there was a lot of power and a lot of heat dissipation. And for that, we actually had to put, as Óscar said, in the MOSFETs. This is the video. You see, this is the MOSFET that each one of them was driving 16 amps. We had a heatsink attached to it. And even so, we have fans pushing air flow to all the heat sinks. So we can run installation for a long time. And the big PCB here, you can see, I don't see, you can see well. Oh, yeah, it's not the best shot. I don't have pictures of the PCBs actually. You can see all the traces were quite thick to support the amount of amperes and current. And to reduce this packet size, instead of soldering the MOSFET to the PCB, because the PCB could add as a heatsink, we had isolated heatsink that they were not touching the PCB, because you cannot connect if you don't isolate it, 2 MOSFET to the same heatsink. They will also short between each other. You always need to have them isolated. So in this case, we had like 3 layers of PCBs, each one with like, I think like 8 or 12 MOSFET of 16 amps, each one of them. So with this, I want to say that powering big things is doable. It's not something that you need to get crazy about. Of course, you have a lot of troubleshooting. It's not the same lighting 1 meter of LED than 200 meters, but it's something that you can do, and it's affordable to do it. Affordable, I mean the way of the effort, not on the price. That will depend on what you want to do. But that with proper design and with proper thought of the wire sizing, calculation, looking for the datasheets of the components, you can do it.
And what's the rules for the width of the traces?
Sorry?
Is there any calculation for the width of the traces, or it's just make them big?
Actually, KiCad, if you have if you use KiCad,
yeah, with the net sizes and stuff.
So there's if you open it, there's a small symbol on the right hand side that it looks like a calculator, and there are tools in there that give you calculations for track width in different layers depending on your power. Also voltage dividers and sizes for if you're looking to calculate antennas and these type of things. So there's like a little calculator in there and the different tabs, and you can see the width, the necessary copper that you need for that. Edu, do you know the thickness of the copper that we have in the PCB in
the lab?
Yeah.
Actually, the board is 1.6 millimeter, and the PCB copper I think is 0.15. It's in inches. Actually, I don't know in millimeters, but more or less it's like 0.15 millimeters. 0.15. Yeah, 0.12, 0.15.
Okay.
I don't know
Because
exactly.
that is also an input. So not only your track width, but how thick is the copper. It's also necessary for you because at the end you have a cross section that is a rectangle.
Here,
and that is
inventory, we can look for it. FR1, FR1 single board, and this is the dealer, no? Circuit board, beacon graphic, low-vinyl laminates. I suppose it's one of these numbers. No?
0.062 maybe in inches.
Yeah, more or less 1.
It's it's 15. Oh, sorry, 0.2.
It's 0. Yeah.
Yeah. So in KiCad, you will see that you input the current that you want to put into the copper. Overestimate that by a factor, either like we call it in engineering, it's called like safety factor, 1.5 maybe, 10 or 2, and then put your that thickness, and then it will give you the top layer track width and the middle layer track width. Of course, depends if you are on outer layers or inner layers, that you will have more or less heat dissipation. And the outer layers normally are thinner. If you, in our case, for example, we can use thinner traces because we are in the outer layers of the PCB.
Cool.
Okay. So that's it for today. I hope we like it. You like it? We hope you like it.
Yeah.
Yeah.
Exciting.
So Monday we have something with Cat, with Cam, or?
Okay, Monday is, some of you already asked me a few of them by asking by mail. Troubleshooting Rhino, didn't know how to set up the values properly, etc. on RhinoCam. So Monday, basically, we will connect on the camera here, and we will share screens, and we will try go with your RhinoCam in case you have it, or in case not, I will switch on mine. Santi was setting up a computer to have remote access to RhinoCam. So you can actually produce the CAM files. Let's say I'm going to assist you to produce the CAM files for that session. It's not going to be a masterclass. Okay.
Vale, gracias. Buen fin de semana.
Bye bye.
Buen
Have a good day.
Have a nice weekend.
Gracias. Ciao.
Who's going out?
Bye.
Ciao, bye.
Oh, bye.
Ciao, ciao, guys.